I was trying to download the PDFs, but I was unable to do that. So, uh, if there's anything that I'm going to write, I will write it separately in a file, in a Samsung Notes file. Okay. So, Unit 5, no? Unit 5, what is it? Descriptive statistics. Fine. So, sample mean. Let me just. So what is the essence of descriptive statistics? In probability theory, we will have all the parameters. We'll have information about the population mean, population variance, but in real life, we wouldn't have that piece, that information we wouldn't have. So we'll have to estimate them. So there were like two different kinds of descriptive statistics. Anyways, I'll just all of this is English, English, English. Oh yes, so two kinds of statistics. Fine. Okay, so mean median mode is here. Okay. Mm, Fine. So mean, let's say, see, this is simple. If you're collecting samples, then the sample mean is given by this one. So you just sum them up and divide by the number of observations. That's it. This is mean. So okay. So in unit one, sample mean is done. What does sample mean? You collect some sample data, sum them up, divide by total number of observations. So sample mean. Fine. Uh, in probability theory, there is something called population mean, the mu, the word mu, this letter mu. But sample mean need not be mu because sample mean it could be biased. There could be many other factors that will not allow sample mean to be mu. But then in real life we wouldn't have this mu, right? We can't. Let's say you want to know the height of every person in Hyderabad. You can't uh, talk to everyone and get this piece of information. So there'll always be that. Uh, so you don't have information. So what do? You try to estimate mu. So it looks like something is a good estimate of something else. So that will come later. Fine. Median is the middlemost value. So if you arrange them in ascending or descending order, just take the middlemost value. That's median. And this everyone knows. That is fine. So sample variance. In probability theory, we have variance, which is sigma square. Here we have S square, where S is sample deviation, S square is sample variance. The only difference here is uh, you have divided by n minus 1. You don't have n. Yn minus 1, we will come to that later. It is there. But this is the formula for sample variance. Variance or standard variance is sigma square. That is for the population. This is for the sample. And mind you, if you're using capital letter, it means it's a variable. If you're using a small letter, it means it is some value. This will come into picture later. We'll see. As of now, they're using small letters. It means they're all values because the data that you collect are values, right? the data that you collect. Heights, 100 centimeters, 150, 175. They're all numbers, they're all values. Fine. So sample deviation is basically the positive square root of sample variance. Fine, all of this is fine. So this one here. So the left side is the one that is given in the definition. You can simplify it to other terms. So it will be helpful in calculations, especially the middle one. Yeah, I mean, you can jump from here to here. These two things are very same. But jumping from here to here is a slightly a long process. So how do you jump? You do this process. So they're just alternative forms of sample variance. It will help in calculations. Why will this help in calculation? Because it is very easy to find the sum of squares of all the data that you got, and this is nothing but sum of all the data whole square. So that is very easy to find rather than taking the difference and then squaring it. That is a bit time taking. Anyways, sample variance. So that is also done. Sample standard deviation is also done. Sample correlation coefficient is not a part of the syllabus, so we want to go through that. Questions and all, you can go through them. They're all simple. That is, and you can go through the tutorial as well. That is more nice. You have questions. I've given answers. Okay, motivation. So here they're trying to tell you why are we taking n minus one? Is that what they're trying to do? Mm. Here, if you notice, they said the population is finite, right? So you can ask everyone. There is a possibility, but it need not be that it's feasible. You can ask everyone. Let's say height. Ask their height, and you can find the population variance in simple terms, or population variance. There you'll get 1 by n. But then in sample variance, we instead of taking 1 by n, we'll take 1 by n minus 1 for some reason. So we'll just see. Will they give the reason here? It's not like they're going to ask you why you're using n minus 1, so I wouldn't focus on that now. But you can read. This sample correlation coefficient is not in syllabus, so I will not cover this. I think maths is more of just going through. I mean, you can go through the examples or use the tutorial problems. If if we have time after this entire thing, you can ask me to uh, maybe solve some problems. If we have time, we'll see. Okay, there's nothing in this slide apart from sample mean, sample variance, sample standard deviation. The only thing to keep in mind is in the denominator of sample variance, it is not n, it is n minus 1. We will see a reason, but later we'll look at the reason much later. Okay, let's see what is in this slide. This is in syllabus, yes. I mean, this sums up what is the relationship between the population and sample. If you have if you have information about the entire population, then you can predict what kind of a sample you'll get. But in reality, that is not the case, right? You only have samples, and now you have to deduce what could you have to deduce some parameters of the entire population. What is the average height of all the people in Hyderabad? Like, you wouldn't probably ask every person in Hyderabad, right? So you'll only pick a sample. So that process is inferential statistics, and that is what we are trying to do now. In probability, we'll know what is mu, what is sigma square, but they're all theoretical. We wouldn't know in real life what mu and sigma square are. Okay, fine. English. In Miraj sir's own words, a lot of English MB slides. Okay, so they're introducing something called theta cap. It is a cap. It's a capital letter. Theta is a small letter. This is a capital letter, theta cap. So it's a variable. That is what I was trying to tell. When we use capital letters, they represent variables, random variable. And one more thing to keep in mind is whenever we are collecting samples, we will assume that those samples are IIDs, independent and identical. They come from independent, identical distributions. And when we know that samples come from IIDs, then it will be easier to apply some properties. They will not mention in the question that these are IIDs, but we'll have to assume uh, IIDs, independent distributions, whatever. Fine. So theta cap is some parameter of the population, I suppose. Let's see. Okay, so small theta is some parameter. It could be the mean or variance or whatever. But then in real life, we wouldn't know what this small theta is, right? This value, we wouldn't know. So in order to estimate the value, we are defining a random variable using this capital theta. So we'll see. We'll just go through some examples. So okay, here capital theta is y by n. So y is like the whatever our data that we collected, and then we are dividing it by the total number of people. So y, in some case, it could be the summation of all your samples or whatever. But here they're all variables. How are they variables? Before you collect your data, you're defining this, so it is a variable. After you collect your data, it you get a value. So that's the thing. Variables are variables. They're not values. Values are values. Okay, fine. When you use small letters, they're values. When you use capital letters, they're variables. Uh, so where is all that? Something called statistic and so on, right? Did we cross that or wait, let me see? Okay, yes, it's coming. Statistic. So the theta cap, mathematically, it is basically a function of random sample. Okay, fine. So it could be summation, it could be anything, but it's a function of some random sample variables. In the sense, let's say you're collecting some data from n different people. So capital X1 will represent the data from the first person. Capital X2 will represent from the second person, like so on and so forth. So you have n data points. So these variables will uh, each xi represents uh, what is it? So each capital xi is a random variable which represents the data from the ith person or whatever, and g of this one. So it is a function. It could be summation or whatever. Since we are dealing with variables, capital theta is also a variable. So it's all variables at this point. The moment you substitute values in the variables, then you get a value. For example, capital X1, let's say you're asking the height. Let's say you're asking 10 people, what is your height? And your goal is to find the average height. So capital X1 could be, so you can write capital X1 equal to something. So then it will become small x1. So small x1 is equal to 100 centimeters. Small x2 is equal to, we'll see, maybe it will be better understood using an example. But capital letters are variables, small letters are values. And this capital theta is trying to, it's a random variable, right? So it's trying to estimate the value of small theta, where small theta is the population parameter. Let's see if there are example. Did they mention what a statistic is? Okay, so this theta cap is called a statistic. Why is it called a statistic? Because based on your sample, you will get to know the value of this statistic. And I told that it's trying to estimate something, right? So it will get one more name, estimator. I think maybe we'll come to that. So currently, if you just collect some random sample and let's say average height or whatever, based on the sample, you'll get your average height. So that random variable, average height, this maybe capital H or capital theta, whatever it is, that is statistic. Okay, we'll just look at some examples. Mm, okay, here the function is summation. Here the function is summation. If your theta cap is x bar, which is sample mean, then your g of x1, x2 till xn is basically summation of xi by n. It is a function of all xi's, right? So it satisfies this representation. Your random variable is a function of x1, x2, x3, so on until xn. Here our random variable x bar is a function of x1, x2, x3, and so on. So this is a statistic. Sample mean is a statistic. So before collecting your sample, so before you collect, they're all random variables. After you collect random variables, then they become values. So I think there is a name for that as well. I think we'll see. So yes, see, it became small x bar after you select a sample and substitute the values. It becomes small x bar. Eh, it's the value of the statistic. It's no longer a statistic. The value of a statistic. So any function of x1, x2, x3, and so on is a statistic. These two are not considered statistics because you're not getting them from the sample data. Mu is a population parameter. In real life, you wouldn't have access to this. Even in this case, you wouldn't have access to the this one. What is the standard deviation, sigma? So these two quantities are not statistics because statistics is defined to be the quantity that you obtain from sample data. These two are dependent on samples. Xi's are dependent on samples. So these two are statistics. Fine. Esteem. Okay, fine. More examples. So even your sample variation is a statistic because it is dependent on uh, sample data. Small s square is the value that you get after you substitute your data points, your xi's. In that case, it will be small s square is, let me, this is a random variable. This is a statistic. But then this is the value of the statistic. So if you have data points, what will happen? Capital X will become small x. So this difference will be more prominent in other places. We'll see. And see here, simplification. No, there was one more simplification. You can just go back to the sample variance slide and uh, look at the simplification. So you can either remember this or this. I mean, both of them, if you could. Whichever one is helpful, you can use. Whichever one is mathematically easy to solve, you can remember. This is sample variance. It is also a statistic. Uh, Random sample. Okay, we were talking about random samples, right? Like, okay, you have some random variables x1, x2, x3, and so on until xn. We have n random variables. It is called a random sample if they are independent and identically distributed. Okay, this is what I was talking about, IIDs. So, what do you mean by independent and identically distributed? Independent means x2 is not dependent on x1, x3 is not, basically, all the variables are independent of one another. Identically distributed means they come from the same probability distribution. See, if you're asking about the average height, it means, eh, let's say theoretically you collect information from every person living in Hyderabad. Then finally you will get some probability distribution. But in reality, you wouldn't know what it is. Despite that, we can say that they come from the same distribution because if you're asking about height, whatever probability distribution height follows, based on that only you get. It's not like your height is following normal distribution and my height is following binomial distribution. It can't be that, right? Every if you're collecting data regarding one aspect, it will belong to the same probability distribution. That's why if you collect any sample, it will belong to the same distribution. That's why identically distributed. So you don't have to worry about it. So if you're collecting any random sample, it's understood that they're independent and identically distributed. In real life, this is at least for the exam point of view, but in real life, sometimes the data that you collect could affect the previous data as well. So that is a different story. We are not getting into that. But for the sake of our thing, we can safely say that our random samples are IIDs. They're independent and they're identically distributed. So if there is any probability function representing, let's say, CDF or PDF, if there's any function, because for any probability distribution there is CDF, PDF, and so on. So all of them will apply to all of these random variables because they belong to the same probability distribution. Mm, okay, fine. And notice this. What do you notice here? F capital X1 of X, F, they're all same because they all belong to the same distribution. So that's why capital F is CDF, right? So maybe if we look at an example, are we even looking at examples? Maybe it will come to you soon. But since since all the xi's belong to the same probability distribution, I can replace all the xi's with simply x. So what I'm trying to tell is, why is this not coming? So let's say you have something like probability of x1 less than 5 into probability of x2 less than 5. And if I give you that x1 and x2 are IIDs, independent and uh, independent and identically distributed. I can write this as I can replace x1 and x2 with, let's say, some xi, and I can say that this is nothing but probability of xi whole square. Why am I able to do this? Because I can replace x1 and x2 with xi, because they all belong to the same probability distribution. Whatever is the distribution, some distribution. I don't know what is the distribution. So they belong to some distribution, but it is the same distribution. Mind you, we are still dealing with variables now. Fine, we'll come back to that. Okay. So statistic is basically any. Fine, we'll not get into definitions as well. We'll just see. So we've seen what is a statistic. We have to come to point estimator. Where is point estimator? I'll just wait for that. Random sampling, sample properties. So random samples are basically IIDs, independent and identically distributed random variables. We would like to review some of the properties. All the xi's are independent. Yes. So if they're independent, we know no. We can uh, like if they're independent, we have some properties like okay, sorry for the delay. Like if A and B are independent, we can simply write this as this. So we have so many properties. Okay, not so many. At least this one. This is the main property for independence. So this we can nicely use the property whenever we require it. And okay, this is the second property we've just seen. We can replace if fx1 and fx2 they're the same thing because they come from the same probability distribution. And okay, expectation of xi is some mu. Basically, expectation of each of these random variables must be the same thing. Expectation of x1 equal to expectation of x2. Why is this happening? Because all of them come from the same probability distribution, and every probability distribution will have only one mean, right? You can't have multiple means for the same probability distribution. So expectation of each of these xi's is mu. That is fine. Variance. Oh, variance is sigma square. That is also fine. We understand. So mu and sigma square are population parameters. There are some values. That is fine. In reality, we wouldn't have access to this. We're just assuming. In theory, there is some mu. Mu of what? For this probability distribution, there is some mu. Like if you're collecting, let's say if you want to check the temperature, you would assume this random variable, which is let's say capital T, which represents the temperature. It follows some distribution, but we don't know what it is. Theoretically, we're assuming it follows some distribution. It has its own population parameters. Now, in real life, what are we supposed to do? We want to find approximately what is that. Okay. We'll come to that in the estimators part. Maybe it will be more clear there. In estimators, will come. You want to estimate something. Sampling distribution. Okay, we know sample mean. Approximate the distribution of sample mean. Okay, we know this is sample mean. Mean and variance of a sample mean is given by something. Okay, so it's like let's say you have your sample mean x bar. Your x bar, the value of your x bar will keep changing depending on your sample. Let's say today you collect some sample, you will get some approximate value of x bar. Let's say tomorrow also you collect samples. It need not be the case that you get the same average. Your average keeps changing with respect to your sample, your sample data. So this what is this telling is if you if you keep collecting samples, the average value of the sample mean will be mu. That is what this is trying to tell. So average of x, something like that. So the average value of sample mean is going to be mu, and the variance of this is sigma square by n. I think we came across this. We will come across this in probability distributions after normal distribution. I think. I think there we showed that if xi's are IIDs, I mean, I can show it to you now itself. See, I'll show you. Xi's are IIDs, no? So x1, x2, so on. I can simply write xi's. But anyways, okay, let me write it this way. They belong to some probability distribution. Uh, let's say normal. Should I assume normal? Okay, whatever. They belong to some probability distribution such that expectation of xi is mu, and uh, variance of xi is sigma square. So they belong to some probability distribution. The property of the probability distribution is this one. Expectation is mu, variance is sigma square. Now we want to find the expectation of x bar. Basically, if I keep, you get my point. You know what is expectation? The approximate value, or not approximate, the average value. So if I keep collecting data, what is my x bar going to look like? What is the average value of x bar? This is nothing but expectation of x1 and so on. This summation xn, I can bring 1 by n outside because it's a constant. And I can use the linear property, expectation of x1 plus expectation of x2 and so on. And I know that these are IIDs. Okay, I forgot to mention. Since they're random samples, they will be IIDs. And if they're IIDs, what can I do? I can say that they're all the same thing. So I can just replace them by xi's. So it will be n times of expectation of xi. I just replaced x1, x2, x3 with xi because they all belong to the same probability distribution. And the expectation of any random variable is mu. So that would mean 1 by n into n. Okay, n cancel. Expectation of xi is mu. So expectation of x bar is mu. We don't know from which probability distribution x1, x2, x3, and so on came from, but we know their IIDs, and we know expectation of xi is mu and variance of xi is sigma square. These are population parameters. Fine. What about the variance of x bar? Variance of x bar is variance of x1 plus x2 plus x3 so on till this one. If you remember variance properties, if you take a constant outside, it will get squared. So I'll get 1 by n square outside. Variance of x1, x2, x3, so on, summation. Variance has a formula. Maybe if we go back to that slide, okay, it's like variance of x plus y. Variance of x plus y is variance of x plus variance of y, even if minus is there. This is the same story. uh, plus 2 times covariance of x and y. I think this is the formula. Maybe we can go back and check. But if x and y are independent, then this will become 0. IIDs, so independent and identical. Independent is there. So I can write this as 1 by n square variance of x1 plus variance of x2 and so on. But I know x1, x2, x3 and so on can be replaced with xi. So this is nothing but variance of, okay, let me write it. I will replace all of this with xi. So what I will get is n times variance of xi. Xi is basically the same thing. So x1, x2, x3, they're all same because they belong to the same probability distribution. So finally, what I'll get is variance of xi by n. So I know variance of xi is what? Sigma square. So fine. So this is how we get this. So expectation of x bar is mu, variance of x bar is sigma square by, where is this? N. Okay, you're back. When we go through central limit theorem, then you will see there that this x bar follows a normal distribution. We'll see. We'll come to that later when we come to central limit theorem. And we also know this. So you take a random variable, uh, just uh, in the numerator you subtract it with the mean. In the denominator you divide by standard deviation. Standard deviation here is sigma by root n. Then that will follow the standard normal distribution. Standard normal distribution is mean is 0, variance is 1. So this will be helpful in some problems, a significant number of problems. Knowing that this random variable, see, sum of two random variables is a random variable. So this left side is one new random variable. This x bar minus mu by sigma by root n is a new random variable that follows a probability distribution, and it is the standard normal probability distribution. Okay, anyways, uh, enough looking at this slide. It looks like we spent some time here. Examples. Okay, let's see. There's an example. So you should be able to know how to convert this English how to convert this question in English to a mathematical statement. So okay, estimate the probability that sample mean is greater than 2.5. So that is basically asking us to write estimate the probability that the sample mean is greater than 2.5. So this is the meaning. You have to find the value of that. Estimate the probability that sample mean differs from the true mean by more than 0.5. So what do you mean differs by true mean? If the true mean is here, so differing by 0.5 means it can either go to the right or it can go to the uh, left. So anything is possible. So it's telling that what is the probability that your sample mean is in this range. So how do I write that? I have to write it like this. Sample mean, the difference between sample mean and true mean. Did they say less than or more than? Okay, more than 0.5. So more than 0.5 means it will not lie here, it will lie outside. So what is the probability that sample mean is either here or either here? So the difference between them, you have to use a mod there. This is more than 0.5. Now you have to sit and solve this. See, find n so that sample mean differs from the true mean. Okay, this is less than. So less than means then you simply change the sign. Okay, wait. This is a slightly different question. Find n so that sample mean differs from the true mean by less than 0.5. Okay, so this is like they gave you an equation. You're supposed to find the value of n. What is the equation? They gave, what did they give you? They're like, the difference is less than 0.5. The probability also they gave you. They gave you, it is 0.95. Now you have to open this and then n will come into picture. Like how will it come? This is nothing but p of minus 0.5 greater than x bar minus mu. This is there. So I want to if you remember x bar minus mu by sigma by root n, this belongs to normal distribution, standard normal distribution. No? So that is we have to bring that into picture because that is simpler to solve. So minus 0.5 by sigma by root n. I'm dividing all the sides with sigma by root n. So I'm only changing the things inside the probability. So 0.95 will not get affected. So don't divide 0.95 with uh, sigma by root n. This change happens only in this because this is one inequality, two inequalities to be precise. So don't divide 0.95 with sigma by root n. You will lose marks then. Sir will not be able to help you in that case. Okay, anyways, so this is z. We represent standard normal with random variable z. So sigma, do we have sigma? This is Poisson, right? See now again, Poisson means this is coming from probability distributions. In Poisson, mean and variance is lambda. They gave mean as 2, so variance is also 2, So standard deviation will be root 2. So we have sigma as well. Sigma is root 2. Sigma is root 2 we have to find n, that's it. So that is the question. So you have to solve this equation. You will have to find n value in this. Careful with the calculations. Do we have mu? Yes, mu also we have. Mu is 2. They already gave you because mu is lambda. Lambda is 2. And sigma is under root lambda. So root 2. Nice. So you have to simply solve this equation. So this is how you do this. Convert the question in English to a mathematical statement and start solving it. Fine. Spending time on examples will drain away a lot of time. So I'll simply just go through things. Okay, they've solved it for us. Nice. See, this is okay. They tried to divide it. Uh, so n value, you got some n value. Fine. Will not spend time at examples. You have tutorial problems. You can go through them. Or else, if you have free time, you can just go through them. Fine. Let's see. What is the next topic? Estimator, no? Statistic point estimator. Where is point estimator? Let me see. Okay, okay, we've come here. Point estimator. A point estimate of a parameter small theta is a single number that can be regarded as a sensible value for theta. Okay, fine. So let's say there is some parameter. It could be mean, variance, or whatever. So there is some population. How do you? So population has some characteristics. So it could be mean, it could be variance, it could be anything. Kurtosis and all that, so on and so forth. Skewness. So many parameters will be there for that. In reality, we would not know what they are exactly. So what we'll do is we'll define some uh, random variable. What is the purpose of this random variable? You want to estimate the value of this. So in that case, if there is any random variable that's trying to estimate uh, the population parameters, you call them estimator. And let's say you collect some sample and substitute in this random variable, whatever. This is some function of random variable, right? So if you substitute your sample data in this, you will get some value. That value is, uh, let's say, something. So you get some value. Oh, let me write value. Value of. So based on some sample data, you'll get some value. That value is called estimate. So this is some value. This is also some value. So it's like this is the approximate value of the population parameter. These are also some values. These parameters are also some values. So we are trying to take the help of a random variable, an estimator, to estimate something. Fine, enough theory. So point estimator. So let's say instead of mu, sigma square, and all those things, theoretically we're assuming small theta is some population parameter. You want to find some approximate value. So you will take the capital theta, the random variable. You'll call it estimator, point estimator of small theta. Whatever approximate value of capital theta that you get by substituting the data points, that will be called point estimate. Point estimate is always dependent on the sample data that you give to the random variable. So here the random variable is point estimator that will be represented by the capital theta. Small theta here is the population parameter. Uh, Point estimate is basically depending on the sample data, whatever you get, the value of capital theta, whatever you get, that will be the point estimate. Maybe yeah, example will help us. Any example? Okay, so they defined capital X to be number of crashes that result in no. Okay, so capital X is some random variable. They defined some random variable capital X. Now, what they're trying to do, parameter is to be estimated is P. So P is the probability that fraction. Fine. Okay, so if you're not using capital X, I mean, you can use vectors as well, but it's still a variable. The point is it's supposed to be a variable. So here estimator is a variable. What is the variable here? They define something. Proportion of all crashes such that uh, that result in no damage. Okay, so no damage. Okay, number of crashes that result in no visible damage is capital X, and total number of crashes are n. Is that yes? So total number of crashes are n. So capital X by small n will give you the estimator. So this is one random variable. Why is it a variable? Because we did not substitute any numbers now. But what is the estimate going to be? So let's say you start your experiment. This person got small x to be 15. What is small x? It is, see, today if I conduct the experiment, x could be 15. Tomorrow it could be 20. Day after tomorrow it could be 8. So small x keeps changing. But capital X is a variable. It's just there. Capital X is a variable. It represents the number of crashes that result in no visible damage today to the automobile. Okay, fine. So if you notice, capital X became small x because estimate. Estimate is a value. When you're writing values, you use small letters. Today the estimate is 0.6. Tomorrow estimate can be 0.7. The day after tomorrow it can be 0.3. It keeps changing based on the sample. Or let's say today only you repeat the experiment again. It could change. But estimator is just a formula there. It's not depending on the numbers. It's not depending on numbers. It's just a variable. So estimator estimate. Theoretically, if you keep running this experiment infinite number of times, probably then you will get your exact population parameter. But that's not possible, right? You can't do that. Not infinitely many times. Whatever cards you produced, uh, make all of those cards crash into the wall, and then you'll get the exact number. But you won't crash all of your cards. That's foolishness. So you'll just take a sample and use that sample to deduce the population parameter. Fine. Mm, So in case you just crash all of your cars, let's say you produced 10,000 cars, you make all of them crash into the wall and uh, write down the report, then you will get your population parameter. Fine, estimating mean and median. Mm, okay, there is some question. We have some data points. Like in the exam also, we'll get questions with sample data. They will give us the random sample. Even in the tutorials, we have these questions. No, we have random sample like this. They'll give us some values. So we'll have to put our calculators to use. Don't forget to get your calculators. Okay, random sample, we have capital letters. They're all random variables. So variable before collecting data. After collecting data, it is estimate. You get values, small letters. So see, sample mean is a random variable there. Capital X, estimator. Estimate is depending on the data. So for this question, estimate is 27.793. Median, no, it's the middlemost value. If you have an even number of observations, you just take the average of the middlemost. So that is a variable. I think it's instead of writing small x, it would have been better if we used capital X there, right? It would have been much more clear. Okay, notation. X bar is mean, X tilde, whatever that is called. I think it's called tilde. X tilde is median. Fine. Estimate is for this question because depending on the sample. In another question, the sample might change. So your estimate will also change. Estimator. See, estimator will always have variables. See, this median is there. No, I would like to change it. Median should be if I have n. If n is even, then my median should be capital X n by 2 plus. Is that how it goes? 1, 2, 3, 4, 4 by 2. Yes, so that is. I'm using capital X. But if I'm using small x, then you can change it. So there it has to be 10 and 11. Capital X, not small x. The estimate, that is fine. This will depend on the sample. This is estimator. Estimator. This is estimate. Estimator of what? Estimator of median. Before collecting the data, we made a formula. After collecting data, we will find the estimate of median. Fine. Mm, we have other estimators. Fine. Okay, fine. You can solve all of this. Hopefully. Mm, okay, more sample data is here. Sample variance. Okay, is that the question? Oh, it's just an example. Fine. Let's estimate the variance sigma square. Okay, so they want to use sample variance here. Sample variance, this is just an estimator of sample variance. Or should I say, sample variance is an estimator of variance. Yes, so this S square is sample variance. It is trying to estimate something. So it is an estimator of variance. So if you substitute the values, then you will use small letters. You will get a point estimate. This formula is estimator. They're all variables. The moment you substitute values, you will get estimate. So capital S square was here. Capital X square is here. It is estimator of population variance. This is the point estimate of population variance. You substitute the values. If you use something else, this S cap square is not sample variance, but it's like, let's say there is another estimator that uses n in the denominator, then you get something else because if your formula changes, your estimate value will also change. So S cap square got 40.335, but S square got 41.126. And they're telling us that we do not prefer S cap square. We prefer S square, where in the denominator you have n minus 1. And they're like, they will let you know soon why we prefer, or not we, why statisticians prefer S square. We'll see. More topics will come, then we'll get to know. Okay, yes. Properties of a good estimator. So in math, something uh, something about something about the estimator being good is defined. So there is, I think three conditions. We'll see. There are three conditions, I suppose. Unbiasedness. Yes, we'll see. So the topics are coming up. So we have some topics. How do we know an estimator is a good estimator? We'll see. If we understand this, then we'll understand why in sample variance we use n minus 1 in the denominator. We'll see. Okay, so there's something called biasness. So an estimator can be biased or unbiased. We'll see how. So an estimator is said to be unbiased if its expectation value is equal to the population parameter. This is unbiasedness. So if you have any estimator, if its expectation value is equal to the population parameter, then it is unbiased. So what if it is biased? Then how do you measure biasness? So the bias of a estimator is defined as this: expectation of the uh, estimator, whatever it is, so capital theta, estimation of not estimation, expected value of capital theta minus population parameter will give you the bias of estimator capital theta. So okay, so what does this mean? Why should expectation of capital theta be equal to population parameter? It means on an average, if I collect samples, on an average, my estimator will give an estimate that is almost equal to the uh, population parameter. So that is nice, no? That is nice. It means our estimator is not biased. If our estimator is biased, then this will not be the case. It means on an average, the expected value of my estimator will give me the population parameter, which is nice because in real life we do not have this information. We want to have this information. At least give us some average value of the population parameter, then we'll be happy. Okay, fine. So if nothing gets into your head, just remember, if this equation is satisfied, expectation of estimator is equal to the population parameter, then it is unbiased. If it is not satisfied, then take the difference between them. So E of capital theta minus theta will give you the bias. I mean, I can write it in this way also, because constants can be taken inside and outside of expected value. Fine. So unbiasedness is fine. So intuitively, when can you say the expected value of an estimator is equal to small theta? That is possible when uh, uh, this estimator is there, no? So the estimates of that estimator will fall just around small theta. So let me. So if you have some population parameter which is here, when will the average value of some capital theta be equal to small theta? It means let's say the estimates of this I will represent it using theta I. So let me just write theta 1. So let's say today you found estimate is theta 1. Tomorrow you find it's theta 2. Next day you find it's theta 3, theta 4, whatever. So if they lie very close to the theta, it means that average value will almost converge here. So that is when we can say that this estimator is unbiased. Intuitively you could think like that, but this slide is trying to say something like that you have to be centered, you have to be close to that. Anyways, I will move ahead. uh, Examples of unbiased estimator. So they told, what did they tell? Capital X has some mean, it has some variance. They gave you some random sample. They're asking you to show that sample mean is an unbiased estimator. How do I show that sample mean is unbiased estimator of mu? I have to show that expectation of x bar is equal to mu. I think we've just done this previously, no? Random sample, what is random sample? It is IID, independent and identically distributed. So whatever procedure I did before, I did it here, no? It's already on the slide as well. Uh, is this? Oh, we did all of this, no? Here. So we proved it previously only that expectation of x bar is mu. The same process is here. So if you show expectation of x bar is mu, then our job is done because that is what they asked us to find. How do you show it is unbiased? You satisfy the equation, or else you can show that bias is zero. What is bias? Bias is expectation of the random variable minus whatever is the population parameter. So expectation of x bar minus mu. Here it turns out to be zero because expectation of x bar minus mu, that is zero. So bias is zero. Fine, simple. Simple example. One more example. Okay. X be a binomial random variable with binomial. So n is number of trials, p is the probability of success. They gave you some estimator, some estimator they gave you, capital X by small n. They're asking you to show or check or whatever that this estimator is an unbiased estimator of small p. Here, small p is a population parameter, isn't it? Here, small n and small p, both of them are population parameters. So, expectation of x by n. So, 1 by n expectation of. No, it's all simple at this point. Now, what is interesting is we will look at example 8. So, example 8. What is example 8? Example 8 is it's telling that the bias of capital S square is zero. What do you mean by bias of capital S square is zero? If bias is zero, it means it's unbiased. So what does this mean? It means capital S square is an unbiased estimator for sigma square. So that means it is nice. So how do we know? Uh, how do we know that an estimator is good? So the first property that we are looking at is unbiasedness. So capital S square satisfies that. So why is this important? This is important because this only happened because in the denominator we have n minus 1. If in the denominator you have n, then you will get some bias. I think they will show us somewhere. But then keep this in mind. Just because capital S square is unbiased, it doesn't mean S is an unbiased estimator of standard deviation. Here, capital S is the sample deviation, right? But we can show mathematically. Even you can check the expectation value of capital S. You won't get sigma. You won't get sigma. You'll get something else. That means there is bias. So capital S square is unbiased, but capital S itself is not unbiased. So that's what they wrote here. Capital S is a biased estimator of sigma. But capital S square is nice. Capital S square is an unbiased estimator of sigma square. Proof. So okay, we are using an alternative form of sample variance. That's why I've shown there were three different forms. One was a definition and there were two other forms. This is the third form, I think. Third, yes, I think second or third form, whatever it is. Fine. So if you do some math, you can see finally expectation of capital S square we got sigma square. This is basically the criteria, right? If this equation is satisfied, it means your estimator is unbiased. So capital S square is unbiased. So because capital S square, what is capital S square? Capital S square is the estimator of sigma square. Here we proved that the expected value of capital S square is itself sigma square. So it is unbiased. You can do the same process for capital S. If you take the expectation of capital S, you won't get sigma. You'll get sigma something. That is a problem. And let's say, okay, maybe let's see uh, in the denominator, if n is there, then that will be a problem. Okay, yes, so that is, so if you notice, uh, okay, so if you notice, what is happening? If in the denominator you have n, see, I know s square is 1 by n minus 1 summation of xi minus x bar square. Let's say I have something else called s cap. That means it has a n in the denominator, and let's see what is the bias of this. I can write s cap in terms of s. So if I multiply by n minus 1 and divide by n minus 1, I will get n minus 1 by n s. So s cap is nothing but n minus 1 by n s. That is what they wrote here. So what is s cap? S cap is basically sample variance, but in the denominator instead of n minus 1, we have n. So not I, it is expressed. What is expressed? S cap square is expressed as uh, uh, S cap square is represented in terms of S square, capital S square. Now we are trying to check the expected value. So n minus 1 by n is a constant, so I can bring it out. And I know that expected value of capital S square is sigma square. That is what we saw previously. Expected value of capital S square is sigma square. So finally, expected value of S cap square is n minus 1 by n into sigma square. So it is not exactly equal to sigma square. So there is a bias. So bias, how much is the bias? You just take the difference between this one and sigma square. So bias turns out to be minus sigma square by n. That is the problem. So this is not unbiased. This is one of the reasons, or maybe this is fine. This is one of the main reasons why uh, in sample variance in the denominator we take n minus 1 but not n. So in the exam, Sir told himself, so in sample variance, if you use n in the denominator, then Sir will straight away cut your marks. He's not going to consider anything because you can't be like, sir, I used n, just n minus 1, I forgot. Sir himself told he wouldn't consider. So be careful. Whenever you're using sample variance, be sure to keep n minus 1 in the denominator. Sir seems to be very I mean, he's steadfast. He's like he's determined. Like he's not going to change his uh, mind on that at least. Fine. Anyways, so uh, bias. Okay, we've seen biasness. Is there anything more in this? Okay, you can check S as well. S is a random variable. Yes, S is a random variable. Is it biased? It is biased. So what did they do here? We know that S is a random variable. So variance of S is non. Okay, variance of S is positive. Fine. And variance of S is expectation of S square minus expectation of S whole square. Okay, fine. And expectation of capital S square is sigma square, that we know. Uh, okay, so they did some math. It might just fly through your head, but or it might not, which is good. But just see, so they've just used some. They just started with variance of S is greater than 0 and finally ended at expectation of S is less than sigma. So, what does this mean? It means expectation of S is not sigma. And what does that mean? That means that's biased, it's not unbiased. Because if it is unbiased, then you will need equality there. Expectation of S should be sigma, but here that's not the case. So, this is one kind of a proof. Maybe you could start from expectation of sigma and calculate the exact bias. But this is one smart way of doing it. But anyways, is an unbiased estimator of sigma square, but capital S is not an unbiased estimator. Capital S is a biased estimator of sigma. Fine. Okay. Principle of unbiased estimation. What is that? When choosing among different estimators. Select. Okay. Okay. So you will have multiple estimators. So what is a good choice? A good choice is basically the one that is unbiased. Okay, so they're asking you to show, are these estimators unbiased or not? Okay, fine. All these are questions you can. Principle of minimum variance unbiased estimation. Among all estimators of theta, a small theta is a population parameter. Choose the one that has minimum variance. The resulting capital theta is called the minimum variance unbiased estimator. Okay, so let's say you have multiple estimators and all of them are uh, unbiased. So among these unbiased estimators, which unbiased estimator should I choose? So here there is something called principle of minimum variance unbiased estimation. It's like choose the one that has minimum variance. So this is like one more property. If it is unbiased, okay. Is there anything more? So you choose the one with minimum variance. Okay, we'll see. So minimum variance means what does it mean? It means all the data points are like around the central point. So here the central, let's assume small theta is mean. So most of the points will be around that. That means variance is less. This tall graph, this tall portion, that has very less variance. If variance is more, it means the data is much more spread out. So you'll have this flat curve. We want to choose our estimator in such a way that whatever we get, no, it should be centered around the small theta. So that is the intuition. That is the idea. Square because you square something. So maybe okay, fine. Mean square error. Error. However you want to remember, you remember it. So if you do some simplifications, if you open all of this, what you'll get is mean square error is nothing but variance plus bias square. Oh, bias square. I thought bias. I'll have to check the tutorial then, because I remember writing mean square error as variance plus bias. So uh, I'll have to see. But it is clear, right? Expectation of uh, theta cap minus small theta square. You just have to open the brackets. Just give me a minute. Check uh, mean square. So mean square error of this estimator capital theta is variance of theta cap plus square of the bias. Okay, square of the bias. Check. I don't remember writing the square, so I'll have to check if I wrote the correct answer. Anyways, so fine. So you see the thing, right? So you see where this is going. A good estimator should have less mean square error. So let's say you have unbiased estimators, which means bias is zero. So mean square error in that case will simply be equal to the variance. So if you want to reduce mean square error, what does that mean? In other words, you just want to reduce the variance. So that is essentially the principle of what is the principle? Minimum variance estimation. Okay, yes. Okay. Minimum principle of minimum variance unbiased estimation. Fine. So in other words, now bias is zero. Fine. Now reduce the variance also. That is one principle. Fine. So if you have two unbiased estimators, and if you know the variance between, if you know the variance of each of them, choose the estimator which has the least variance. That will be a good estimator. Fine. Mean square error is just another equation, another formula. Uh, okay. Okay. This is some equation. You can question. You can just solve it. You have one estimator which is just x1. You have one another estimator which is a sample mean. See, estimator can be any random variable. So here theta, capital theta one is simply capital x1. No, it's fine. It is a random variable. So that is one estimator. Whether it's a good estimator or not, they're not concerned. They just gave two estimators. Now we have to find the minimum square error and then compare which one is greater, which one is smaller. They already gave the relation. They are asking us to show that this is true. So it's basically approve that question or show that question. So let's see what happens. What did we get? Are these biased or unbiased? We know expectation of x bar is mu, but expectation of x1 is also mu. So these two are unbiased estimators. If you notice, theta 1 and theta 2 are unbiased estimators. But if you look at it, you feel like theta 2 will be much better. But how do you show that mathematically? You can show it mathematically by just finding out the mean square error for these two estimators. You will find that, what do we find? Mean square error of theta 1 is sigma square, but mean square error of theta 2 is sigma square by n. So which estimator has a less mean square error? The second estimator, because n is, let's say, greater than 1. So theta 2 will have less mean square error. That means it is much more preferable, and that is a much uh, better estimator than theta 1. And our intuition is also telling that theta 2 is looking like a good estimator because it is using all data points. So the more data points you use, the more good your estimator becomes. That is one intuitive way of thinking. Okay, fine. You have more examples. You can, okay, interesting. So minimum, maximum. I think tutorial in the non-assignment questions, one of the first question. I think the first question itself, you'll have minimum and maximum and something like that. So you'll have to see how that is done. Uh, like here, fine. So here what is going to catch your eye is expectation of minimum of x1, x2, x3, so on xn. That is 1 by n lambda. So let me just show you like this minimum maximum. Uh, Someone asked me before, so I already solved it. So let me see if I still have it. Or we can do it once again, but uh, that would be easier. Yes. So we'll do this. So we'll just see why is the expectation of minimum of, okay, let's see the question once. So x belongs to exponential, fine. Lambda is a parameter, fine. So we'll not solve the entire question. What we'll do is we just want to find the expectation so that you people don't get confused or something. Let's just see. The goal is to find the expectation of minimum of, uh, let me write it down. I want to know what is the expectation of minimum of x1, x2, x3, so on until xn. This answer will be 1 by n lambda. We will see why. I'm not asking you to memorize this. All of you know how to, uh, not the procedure maybe. No, okay, fine. I'll just do it. You can see it. So what I will do is I will just start with something. So I will try to first find what is the probability that this is one random variable, right? So what is the probability that this random variable is uh, less than some value small x? So small letter means it's a value. And we know this is, if you read the question once, they're all random samples, right? Yes, so random sample. So they're all IIDs. So what is the information that we have? The information that we have is this xi or whatever, just x. It belongs to exponential, and we know that they're all IIDs because it's a random sample. So that is fine. So what is this going to be? I mean, I can define one more random variable. I mean, it's the same thing, but it is easier for me to write. So I will just define one more random variable. I did nothing here. It's just x minimum. So this is nothing but 1 minus p of, I'll use this later, not now, later. So this is also understandable. Fine, what did I do? I'm just going here and there, going, it might not look like I'm reaching a destination, but anyways, now look at this. What do I mean when I say minimum of x1, x2, x3, xn? What do I mean if what do I mean by saying that the minimum of this is greater than some x? Think about it like this. If the minimum itself is greater than x, it means each and every random variable is going to be greater than small x. So I can write this as probability of x1 greater than small x and x2 greater than or equal to small x. I mean, here equality is there, here also equality is there. That is because exponential distribution is continuous, right? So it shouldn't matter. If it's discrete, then you should be careful. Then equality won't come. But exponential distribution is a continuous distribution, so I wouldn't have to worry about that. So on and so forth, you'll get xn greater than or equal to x. Fine. I told you that xi's are x1, x2, x3. They're all IIDs, right? If they're independent, I can split the thing. So I can use what is it? Uh, it's some axiom, right? I don't know. I don't remember. I think it's one of the axioms of probability. If they're independent, I can split it this way. So I can write it as a probability of x1, capital X1 greater than or equal to small x into probability of capital X2 greater than or equal to small x. So on until probability of xn greater than or equal to small x. Fine, but they're all IIDs, so I can replace x1, x2, xn, and so on with capital Xi's. So if I do that, it will be nothing but xi greater than or equal to x. I'm doing this n times, so we'll get power of n. If you notice, what is this value? I started with this, right? Probability of minimum of x1, x2, and so on is lesser than or equal to x. But if you notice, I can call this the CDF of x min. So what is CDF of x min? CDF of x min is this one, the cumulative probability distribution. That is nothing but x min is less than or equal to small x. That is what I did here. So I defined x min, no? So x min is nothing but minimum of x1, x2, x3, so on until xn. So I have my CDF of x min, which is nothing but probability of xi greater than or equal to x whole power n. Okay, before I go there, uh, before I go there, let me. We know that capital X follows exponential distribution. So that itself has its own CDF, PDF, and so on. So I can rewrite this. I can rewrite this as 1 minus p of xi less than or equal to x. Again, it's continuous, so it shouldn't matter. Equal to can come there. So what is this? This will be the CDF of my exponential distribution because capital X follows exponential distribution. So 1 minus f of x. So x, no? So x or xi, whatever, it's the same thing, whole power n. So I was talking about my CDF of x min, right? CDF of x min is the same value, 1 minus f of xi n. Fine. Now I will find the PDF of x min. How do I find the PDF of x min? I just have to differentiate this CDF with respect to this variable x. So what would that give me? So minus n 1 minus f of n minus 1 into minus differentiation of this one. So finally we got, and if you remember, what is the CDF of exponential distribution? CDF of exponential distribution is this one. Uh, This is the CDF of exponential distribution. And PDF of exponential distribution, simple. You just differentiate this, you will get this one. We know this. This information we'll get from probability distributions. If you remember, you will know. This is the CDF and PDF. If you know one thing, you can get the other one. So you don't have to remember both of these things simultaneously. If you know one, you'll get the other one. Okay, anyways. So 1 minus, okay, I'll just simplify this. So after simplification, at last, what you'll get is, uh, you'll get something that looks like this. After simplification, just substitute the values. After simplification, you'll get this. If you notice, this looks like the PDF of some random variable that belongs to a probability distribution of parameter n lambda, right? Because if you replace lambda with n lambda in this, you will get this. So that means, what does this mean? It means x-min follows the probability distribution. Which probability distribution? Exponential probability distribution with parameter n lambda. So what does this mean? What would this mean? This means expectation of x min will be 1 by parameter. Here the parameter is n lambda, so you'll get 1 by n lambda. So expectation of x min is 1 by n lambda. You don't have to remember anything. If you know how to solve things, it is good, because this value can change, right? Depending on the distribution. Since it is exponential, we got that. If it is some other distribution, you get some other things. So if you know what to do, where to do, why to do, you will get the picture. So if you've gone through this, so maybe we have something similar, I think, in the first question of the tutorial. Not this thing, but we were dealing with x min, x max, all of that, minimum, maximum. Okay, fine. So that is how x the expectation of x min is 1 by n lambda, which is used here. So n times 1 by n lambda. Someone asked me this. I found it to be interesting. That's why I shared it. Interesting. Did anyone message me? Okay, no one. Fine. Okay, so unbiasedness is done. We looked at mean square error. The third property of a good estimator. So consistency. So a good estimator must be consistent as well. So we will look at the definition of consistency. Mm, let's see. Let's see. What is consistency? Okay, we have, and when they say sequence of estimators, what they're trying to tell is, if you have a population, you need not have only one parameter, right? You can have mu, you can have sigma square, and so on. So similarly, you will need multiple estimators. So that's why they're telling sequence of estimators. That's it, or else everything else is the same. So sequence of estimators. So I can club them up and put them in one, uh, like a vector. Maybe I can call this probably theta one, theta two, and so on. I have a sequence of estimators. I club them in. I just kept them in one place, and then I'm referring to the entire thing as a theta cap. So that's why this looks like a vector. A vector looks like this, right? You have multiple components. So okay, fine. Anyways, moving on. Sequence of estimators. It is said to be consistent if something happens. What is that something? As n tends to infinity, the probability that what is this? The difference. So the probability that the difference is greater than epsilon is zero. Okay, what is this difference? The difference between uh, the estimator and the population parameter. So as n tends to infinity, this should be 0. So what does that mean? In other words, it means so epsilon is some small positive number. Epsilon is some small positive number. As n tends to infinity, the probability that the difference is greater than some small positive number should be 0. That means theta cap should be equal to theta. Maybe that is what it's trying to tell. The modulus of, okay, fine. So that is what it's trying to tell. So if the probability that it's greater than epsilon is 0, then the probability that it is less than epsilon should be 1. That would mean, see, epsilon could be a very small number, very close to 0. So if epsilon, if something is, see, modulus of a number will be, let me just write it once. So the probability of, okay, let me not say it out. The probable, as n tends to infinity, the probability of this modulus being less than epsilon, where epsilon is a very small number but still positive, this should be 1. So what does this mean? Uh, this modulus is a positive, not positive. Modulus is a non-negative number. Epsilon is a positive number. It's like let's say I have modulus of something. It will look like this, right? Modulus of something will look like this. I'm saying it is less than epsilon. So epsilon is there, no? I'm dragging this down. I'm dragging the epsilon down. It means this modulus value should tend to 0. That is the meaning. If I drag the epsilon down, it means my modulus value is decreasing. It's tending to 0. You get my point, right? Something like this. So what do I mean by this is tending to 0? It means it's like something like this maybe. But I'm not writing equal to, because this is a variable and this is a number. So I'm not writing equal to. Let's see if there are any examples to. But the idea is this. The idea is that the difference uh, can't be greater than some positive number. That's why, what do I mean by can't be? I have to simply say the probability is equal to 0. What do I mean by n tending to infinity? It's like if the number of samples that you're taking tends to infinity. Let's say you're interviewing 100 people, 1,000 people, 1 million people, then the chance that your estimator is going to give you the population parameter, that chance is going to increase. So, or the difference being greater than epsilon is going to decrease. So something like that. Anyways, maybe the theorems that will come afterwards will be of some use. Lemma, okay, lemma, not theorem, lemma, fine. I think the lemmas will be helpful in solving questions than this one. But just in case, if they ask you what, I mean, I don't think they're going to ask you. But it's just two simple lines. It's the same thing. But the one that is going to help us more are the lemmas here. Let us look at the lemmas. What does the lemma say? Questions will maybe come from lemmas than here, because I don't see how do you solve anything using this. But just keep this in mind. It's like that epsilon delta definition, but fine. We use the epsilon delta. Okay, fine. Anyways, we're going off track. We'll just see. We'll look at the lemma. What does the lemma say? If theta cap is a sequence of unbiased estimators, okay, bias is equal to 0, and limit n tends to infinity of variance is 0. Okay, it means, okay, now see, look at this. We know mean square error is variance plus bias square. They said the theta cap is unbiased. It means bias is 0. So what is mean square error now? Mean square error is equal to directly variance. Now they're telling that n tending to infinity, variance is 0. So it means if your n is a very large number, your variance should tend to 0. That means my mean square error is tending to 0. So the story here is they want to reduce mean square error. That is the story. Then it becomes consistent. That is the story here. So consistency is basically mean square error being 0. This is much simpler, right, than whatever was before. But from here only you will get this. This is the main definition. From this definition you will get this lemma somehow. But this lemma is easier to digest. So, anyways, so if you have unbiased estimators, then and then if the variance is tending to 0, or in other words, if n is tending to infinity, variance should tend to 0. Uh, then that estimator is consistent. I mean, there is a proof as well. You have to use the definition there. So they use the definition by using the Chebyshev inequality. That is out of the syllabus, anyways. So we'll not look at proofs. They're not going to ask us to prove the lemmas or whatever. Okay. So finally, what is the takeaway from here? If you have unbiased estimators, and if the variance is tending to 0 for large n value, basically when n tends to infinity, then theta cap is a consistent estimator. The next lemma will be a very generalized lemma. What if the estimator is not unbiased? Why is this stuck? What if, yes, so there is no mention of unbiasedness. So it can be biased or unbiased, we don't know. But the story is this: you want to reduce mean square error. So that is what we've seen. If it is unbiased, then bias is 0. Then mean square error is basically variance. That's why you want to reduce variance to 0. Here the story is more general. What is the story? You want to reduce mean square error. So as n increases to as n tends to infinity, your mean square error should go to 0. That is the story. If this is satisfied, then you call your estimator consistent. So proof we will not go through it. You can go through it, but you don't have to go through it. So we are least bothered about it. Uh, Example, okay, maybe we'll see some examples. You have mean is given, variance is given. They gave the estimator, which is sample mean here. They're asking us to show if this estimator is a consistent estimator. How do you show that? You can show that x cap is unbiased. Then if you show it's unbiased, then you can say that mean square error is equal to variance. You can find the variance as well. So variance is nothing but sigma square by n. We did that also. Before all of this, we found the expectation of x cap and variance of x cap. As n tends to infinity, it is very much obvious that variance is tending to 0. Therefore, x cap is a consistent estimator. Nice. Sample mean is always consistent for the population mean if the second movement exists. Second movement in the sense basically the variance, I suppose, but we'll see. Is moments a part? Okay, no. MGF and all are out of syllabus. Moments is also out of syllabus. Fine. So we'll not discuss about that. Okay, proofs are fine. We are not going to look at proofs. And Chebyshev and Markov's inequality are not there. Consistency of S square. Okay, now we are checking the consistency of S square. Uh, we've we've heard good things about S square. S square, capital S square is unbiased. Capital S square is this. Capital S square is that. Now we'll look at its consistency. We'll look at its consistency. Turns out capital S square is consistent. Okay, nice. But here they're using the theorem. Is there a way to use the lemmas? You should be able to use the lemmas. How do you use the lemmas? You should basically find the mean square error of capital S square, which is nothing but the variance. So if you find the variance, I think your job is done because we know that capital S square is unbiased. So what is the variance of capital S square? What is the variance? Oh, okay, fine. Okay, I let me write some things on the screen. Let me write some things on the screen. Let me write some things on the screen. This will come at the very end when we are talking about confidence intervals. Uh, yes, so I'll write three things on the screen that will basically summarize everything from I think basically confidence intervals. Yes, so that will summarize confidence intervals and probably most of. Oh, fine, fine. Enough talking. I'll just write three things. These three things will come back later on. So we know that x bar minus mu by sigma by under root. We know that this follows normal distribution, standard normal distribution. This is fine. There is one more random variable. Let's suppose we don't have sigma. We don't know what is sigma. So what do you do when you don't know sigma? You will use the sample standard deviation. We know it is biased, but we have no other choice. So we will use the sample standard deviation. Everything else is same. We don't have mu. Here mu is unknown. Not mu. Sigma is unknown. Sigma is not known. Then in that case, what is this uh, random variable? What is this? What is the probability distribution of this? Turns out it's going to be a student t distribution of the n minus 1 degree of freedom, which will come at the very end, but we'll see. Student t distribution of n minus 1 degrees of freedom. The proof and all, we don't have to go through it, but it's in the slides. We don't have to go through it. That's fine. So I'll just write the three lines summary. Why did I stop the explanation is because there is a distribution for this. N minus 1 s square sigma square. This follows chi-square distribution. Chi-square distribution appears after gamma distribution in probability distributions PDF. So chi-square distribution of n minus 1 degrees of freedom. So these three things will help us. The last two things, or maybe okay, fine. These three things will help us mostly in confidence intervals. But if you notice, this is a random variable following chi-square, right? So if we know the distribution, we can find the expectation as well as the variance, right? So in this case, expectation will be uh, how much? I think n minus 1. Uh, yeah, I think yes, so n minus 1, I think, and then variance will be twice of that for chi-square, I think. Let's see. Mm, let me just see. Let me just see. Because it's good to know expectation of chi-square. Okay, this is only the thing. Fine. So this is the okay. Fine. So expectation of this is expectation is equal to number of degrees of freedom. Variance equal to twice the number of degrees of freedom. Fine. All of this is fine. So I was telling you. Okay, where were we? Uh, we want to find out the consistency of s square, right? Consistency of s square. So we want to use the lemma instead of using the definition. Lemma is easier, right? We want to find mean squared error. We know that the bias of s square is 0. We know, we've seen. We know that s square is an unbiased estimator of sigma square. So now mean square error basically becomes the variance. So what is the variance of s square? We don't know, but we know the variance of this. So what I'll do is uh, variance of n minus 1 s square by sigma square to sigma square by n minus 1. No change. This is essentially variance of s square. So I'll take the constants outside. What will happen? Sigma whole power 4 n minus 1 whole square. The constants get squared, right? You'll get variance of n minus 1 s square by sigma square. We know what is the variance of this one because this follows a chi-square distribution of degrees of freedom n minus 1. That would mean the variance is twice of that. So n minus 1 square. Variance is 2 times n minus 1. So finally, the mean square error, which is equal to variance because bias bias square is 0, that is fine. So finally, you will get this one 2 times. So as n tends to infinity, or else you simply write n tends to infinity, mean square error of this one. This is nothing but basically, see, it goes to 0. So that means s square is a consistent estimator. So you don't have to use the definition. We can use the lemma to show that s square is a consistent estimator. Because if you're using the definition, then the Chebyshev and Markov's inequality comes into picture, and those are out of syllabus. So we will not use them. You have to use this one. So extra information, not extra. This is still there. This will come at the end though. With all these, not all these. The last two will come at the end. The first one we already know. So what is the problem here? Here mu is not okay. Fine. So fine, fine. So nice, beautiful. Uh, Expectation of fine, fine. We'll just continue. We'll see when this comes up later. Mm, what is the next topic? Invariance. Okay, we'll see. What is invariance? Okay. If t is a consistent estimator and if f is a continuous function. Okay, so function of the random variable is also a consistent estimator, provided it's a continuous function. Fine, nice. So what is the implication of this? It means now my capital S is a function of s square, right? S square is consistent. So small capital S is a function of that capital S square. It is a continuous function. So capital S becomes a consistent uh, estimator. Nice. So using this theorem, we can say capital S is a consistent uh, estimator, provided we provided it is known that capital S square is a consistent estimator itself. Okay, exercises. Nice. Sitting on a chair doing exercises. Okay, we have questions, references. Well, I didn't think it would have taken a lot of time. Okay, how much time is left? 2, 3, 4, 5. Okay, so much time. Fine. 5. We should wrap this up fast. Maximum likelihood estimation. Oh, this is that you should define something called L. English finding good estimator. Yes, we've seen unbiasedness, minimum square error, consistency. No guarantee that unbiased or consistent estimators exist for all parameters of interest. Okay, we will just get into it. There's something called maximum likelihood estimator. It's like the fourth uh, property, I think. So likelihood. So there's something called likelihood. So we'll see. And you want to maximize likelihood. For that, we have to first of all define likelihood. So we'll see. What is likelihood? Uh, okay, so if you write the okay, this is probably uh, discrete. So you have PMF, not PDF. So your PMF is a function of x and p, where this is binomial. So your x is but binomial is out of. Okay, so I think Sir himself said, right, out of syllabus means you won't get direct questions, but you can get questions indirectly. So yes, so fine. So binomial discrete probability distribution. The PMF of binomial is a function of x and p, where x is the number of successes, p is the probability of a success. Probability of success. So what this person is doing is this is now the likelihood function. So I can just replace f with that. Okay, we'll see if there's an example. Likelihood. Yes, so there is a function called likelihood. There's a function called likelihood, capital L. It is a function of p. We are treating p as a variable. The other factors, which are small x1, small x2, small x3, and so on, they are all values. And since we are dealing with random samples, they're all IIDs. So I can split the PMF. So initially, uh, it's like P of capital X1 equal to small x1, capital X2 equal to small x2, and so on. Since they're all random samples, I can just split them apart. It will become a product. So finally, you will get small p of small p power summation. Okay, all of this is fine. It's just math at this point. So this will be my likelihood function. This will be my likelihood function. And based on the sample data, I will get summation of small xi and summation. Okay, there's only one thing, summation of small xi. I will treat my p as a variable. So I will differentiate my likelihood function with respect to p and equate it to 0. What does this mean? It means you want to find an extreme value. Extreme value means either maximum, minimum, or saddle point. But we want to maximize the likelihood function. That's why maximum likelihood estimator. Am I still live? Okay, yes, I am still live. Yes. 1 minute, let me just. Okay, anyways, nice little break. Uh, okay, 1 more minute. Sorry for the interruption. Some messages. Anyways, what was I telling? You have a likelihood function that is a function of p. Uh, we'll see some examples, but in this case, it is p. We want to maximize this. So you take the derivative, equate to 0, solve for p, you get some answer. So what did we get? We got that p is supposed to be summation of small xi's by n. This is nothing but small x bar because they're all values, right? So looking at this format, we can find an estimator for p that will be nothing but you replace the small letters with capital letters. Uh, x, I mean, n is simply n is not a variable, n is always a constant. So you replace a small x with capital X. That will be your estimator. What kind of an estimator is this? It is your maximum likelihood estimator because you did some process that increased the likelihood. Uh, okay, anyways, I was telling that if you take derivative and equate to 0, you will get maxima, minima, or saddle point. How do you know it's maxima? How do you know means you do the second derivative test and check if it is less than 0, which is given here. But then that will take some time. So Sir himself told that you don't have to do the second derivative test to check if it is a maximum or not. So you can simply equate the derivative to 0, and whatever value you get from there, you can consider that to be maximum. No need to do the second derivative test in order to prove formally that this is indeed the maximum value and it is not minimum or saddle point. You don't have to do the second derivative test. Fine. So what did we see here? You will get something like this. This is your estimate. This is your estimate. Estimate for P. Estimator for P you will get by replacing the sample values with capital X, capital letters. So what people do is before doing all of this, here itself they will substitute the numbers because we have the numbers. So here in the likelihood function itself, people will find the summation and substitute it here. So p power some 200, 1 minus p power, let's say n is 300. 300 minus 200, 100. So you don't have to substitute the numbers. You can do it, but the benefit of not substituting the numbers is when you get the estimate of p, you will get in terms of small x. So directly looking at the structure of the estimate, you can directly write estimator. But if you substitute the values in the likelihood function itself, then you have to again solve the same thing to find the estimator. That is time taking. So the suggestion here is do not substitute the values in the likelihood function itself. After you get the estimate for p, then you can substitute the values to get the estimate. And now directly you can write the estimator. Just change small letters to capital letters. If you look at an example, maybe okay, one more way is not one more way. A way that is going to simplify our process is before differentiating your likelihood function, just take the log of the function and then you differentiate. So this will simplify some things. We will not have to uh, do more math in that case. So here, instead of taking the derivative of likelihood function, we are taking the derivative of log of likelihood function and equating that to 0. So you don't have to solve LHS, simply solve RHS and equate it to 0. You don't have to write uh, what is this? You don't have to write 1 by log p because differentiation of log p, I understand it is 1 by p. Sorry, differentiation of log p, we all understand it's 1 by p, but you don't have to do that. You don't have to do that. You just have to differentiate the right hand side, equate to 0, and solve that part of the equation. Uh, in the tutorials, I think if you look at some solutions, I use this log thing. So maybe if you look at it, you'll get some idea, or you might have gotten some idea just to sharpen that idea, whatever, without any doubts, without any confusion. Because the mistake, Sir himself told this. I'm not telling this. Sir told that sometimes in LHS people will start writing differentiation of log. Where is log? Uh, yeah, so differentiation of log LP is 1 by LP. That is one thing you have to be careful about. You should not do that. So what Sir did is Sir replaced ln of LP with some small LP. So this is your new likelihood function. So maybe you could think of it that way. But you don't have to open this. You don't have to differentiate this and write 1 by LP. 1 by LP is equal to so on and so forth. You don't have to do that. Okay, anyways. Formal definition. Okay, fine. Let's see. What is the formal definition? So you have some random samples, random variables, capital X1, capital X2, fine. So parameters, okay, fine. Unknown parameters in the sense maybe you're collecting some samples, so you'll get some values. That's why small thetas are used here. So small theta 1, small theta 2, some values. Okay, let's say some PMF or PDF is there. So f of x, small theta 1, small theta 2, all of that is fine. So your likelihood function is going to be the joint PMF, I think. Yes, so uh, what is happening? Mm, it's better if you look at an example, if all of this is passing through your head. Uh, okay, this is one way of thinking. Okay, let's look at an example. Let's say you have some random sample. They've given some PDF. PDF, yes, so continuous distribution. Find the maximum likelihood estimator. 1 minute. Just 1 minute. Just 1 minute. Okay, we were looking at an example, right? So likelihood function is basically uh, is there any sample? No. Okay, there is a sample. Okay, random variables, fine. So it's like, let me just write that. So you have some likelihood function. let's say in this example, what do you have? You have a PDF. You have a PDF that is dependent on some value, so you get some value. Fine. So that is exponential, right? In the PDF, we saw theta. Theta was some parameter. Fine. So likelihood function will be a function of that theta, and there were some random variables, right, which represent the random samples. So if you take a sample, I will get small x's. So this is some sample. So my likelihood function is going to be function of this theta and these values. These are values. These are variables. So my likelihood function is going to be a function of all these things. So that is equal to what? What is this equal to? It's nothing but it is equal to f of x1 equal to small x1. It's like the joint PDF at this point, and so on until capital Xn equal to small xn. But since this is a random sample, I can split this up. If I split it, what will I get? I will get f of this one into so on. You keep multiplying f of xn. They're all IIDs, so I can replace x1, x2, x3, so on xn with xi's. So I will get f of xi equal to small xi. I'm doing this n times, so whole power n. Where is this theta means? In the question it's there. So the PDF has theta, so from there theta will come. So it was, I think, 1 by theta e power. Okay, so e power minus xi by theta. This is your likelihood function, but what you're supposed to do is you're supposed to treat the values as a constant and treat this parameter theta as a variable. And then you differentiate with respect to theta and equate it to 0. What do you gain by that? You're trying to maximize theta now. Uh, maximize theta? No, you're trying to maximize the function, which is the likelihood function. And what is this? Yes, so if you differentiate this function with respect to theta and equate it to 0, you want to maximize this. But the simpler way is first you take log and then you differentiate. So if you take log, you will get something. Now, okay, now your new likelihood function is ln of capital L of theta. Fine. So you will get something if you solve, if you keep solving. If you keep solving, you will get theta. So what does this theta represent? This theta represents uh, uh, that value. This is that value of theta that maximizes the likelihood function, which was the PMF, or in this case PDF, because it's continuous. So looking at this, I can write my estimator. You don't have to do the second derivative test. That is fine. You don't have to do the second derivative test. So looking at my estimate, I can write my estimator, which is nothing but I replace my small letters with capital letters. Uh, okay. Here they did not give any sample, but if they give any sample, I can substitute it in my estimate. Where is this? Here, I can substitute it here. Fine. Okay, here you have two thetas. So you have two parameters of the population, where theta 1 is the mean. So because normal, mean comma variance, right? So theta 2 is the variance of the population. So here you will need to do two things. One is differentiating with respect to theta 1. The other one is differentiating with respect to theta 2. But it's just the same likelihood function still. You just have one likelihood function, but then you'll have two variables in that. Uh, so this is the likelihood function. What? How did we get this? I just kept multiplying uh, like capital X1 equal to small x1, capital X2 equal to small x2, and then I wrote the PDFs for everything. Whole power n will come, and this is what you get at the end. Uh, they okay. So logarithm was taken, and then differentiated and equated to zero. Differentiated with respect to what? So you differentiate it with respect to theta one. The other cases you differentiate with respect to theta 2, equate to 0, solve. So you will get theta 1 and theta 2. You'll get the estimates. So theta 2, you got some estimate. Theta 1 also, where is theta 1? Oh, theta 1, you got x bar. Fine. Looking at the estimates, I can write the estimators. Just replace small x with capital X. So you will get your estimators. If you notice, the maximum likelihood estimator of mean is the sample mean, but the maximum likelihood estimator of variance is not the sample variance. If you remember, this was the uh, here this is nothing but n minus 1 s square by n, or this is that variance which uses n in the denominator, and we know this is biased. And is this consistent? No, I mean, you can check. It is consistent. Consistency is basically mean square error. That is a different story. But the conclusion here is just because it is biased, or just because it is unbiased doesn't mean it's the maximum likelihood function, maximum likelihood estimator. In this case, the other. Do you want to give a name to this? What would you give this? Uh, I don't know. Okay, I'll call it the other sample variance. Here, the other sample variance is the maximum likelihood estimator. We know this is biased. We know this is biased. But the which one? The original, the proper sample variance, that is not a maximum likelihood estimator. That is fine. That is biased. That is consistent. All of is it consistent? Yes, yeah, that is fine. That is biased. That is unbiased. That is consistent. All of that is fine. But that is not the maximum likelihood estimator. So careful. So this is here, this theta 2, which is the other sample variance. This is a maximum likelihood estimator. The other one is not a maximum likelihood estimator. So this is an interesting conclusion, because this came, the sample variance did not come. This sample mean is chill. It has no conflicts whatsoever. Okay. Anyways, moving on. Okay, some exercises you can just see and solve. Look at the tutorial problems. Uh, Fine. All of this is nice. The same thing again and again. Just find likelihood function. Oh, you have 82 slides at this. Okay, time to uh, increase the pace. You have questions and questions and questions and examples. You can go through examples. Maybe then you will get the feel of how to solve for likelihood functions, maximum likelihood estimators. Is there any conclusion here? Okay, asymptotic properties in the sense when n tends to infinity, then uh, okay, we'll see. We'll see asymptotic properties. We'll see. So they're saying that MLEs have asymptotic properties. We'll see what the properties are. It's saying that if n for a maximum likelihood estimator, if n tends to infinity, then the estimator will be asymptotically okay. Then estimator will be consistent. In other words, estimator is asymptotically consistent. I will repeat: estimator is asymptotically consistent when the following is true. As n tends to infinity, the estimator is tending to be consistent. So they wrote the definition of consistency here again. We can use the lemmas that we know. We know some lemmas, no? What are the lemmas? As n tends to infinity, mean square error should be 0. That is one lemma that we know. If we solve that, we can know if the estimator is consistent or not. Asymptotically unbiased. Same thing. As n tends to infinity, estimator tends to be unbiased. As n becomes large, the estimator is approximately around. Okay, okay, the interesting property. As n becomes large, the estimator tends to be a normal random variable. And therefore, the random variable, this one converges to, okay, nice. Because if we say as n becomes large, this estimator tends to be unbiased. So its mean will then be the population parameter itself, which is theta, which is theta. So I wrote here theta. So mean is theta, uh, capital theta minus small theta by under root variance. This is nothing but the this is very similar to uh, we'll see. This came after normal distribution. So if you have a random variable minus mean divided by standard deviation, that will give you uh, standard normal under some conditions. The condition is this estimator, whatever is a random variable, that should be normal as well. So a normal random variable minus its mean divided by its standard deviation should give you the normal standard normal variable. Normal standard normal should give you the what wait, let me be slow. So normal if you have a normal random variable, you subtract it uh, you subtract its mean from it and divide it by its standard deviation. This new random variable will follow the standard normal distribution. Fine. So how do I know small theta is its mean? Because this capital theta is asymptotically unbiased. As n becomes large, its mean will become theta. Uh, Fine. All of this is fine. So properties of maximum likelihood functions are these: it is asymptotically consistent, asymptotically unbiased, and it tends to be a normal random variable. Normal random variable following this one. So it's a normal distribution. Mean is going to be theta. Variance is just the variance. What is variance going to be? It's maximum likelihood, right? And we said it's asymptotically consistent. If it's asymptotically consistent, that would mean wouldn't variance go to zero? Wouldn't variance go to zero? Okay, fine. I think I have a good question, but we will not go into that. We'll just go on. We'll just go on. Interval. Okay, yes. So interval estimation. So until now we've been um, using the word point estimate, point estimator. I did not use it much in the video, but if you look at the slides, so estimator, estimate, they're all point estimates or point estimator. Now we look at interval estimations. So that is the difference. The reason there was this word point was because there is something called interval estimation. So that is what we're going to go through, and specifically we will look at uh, confidence intervals. They're not different things. It's like you have an interval. Now you want to. Okay, we'll just see. We'll just dive in. We'll see what is there. We'll dive in. Motivation introduction. I mean, at this point, if you simply remember the formula and just know how to use them, all is well. You don't have to read any of this. So I think that's the best thing that we can do now. So I'll just get inside. I don't have to tell everything, right? Um, okay, so maybe something I can tell, but we'll see. Okay, just 1 minute. Okay, I'm back. Um, uh, where was I? Okay, we were trying to do a confidence interval, right? Let's see. Do you even have to read all of this? Okay, I think I can start from the graph. Uh, how do I begin? How do I begin? Okay, so uh, fine. I'll start from this example. Let's say our random variable is a standard normal variable, and the interval is minus z alpha by 2 to z alpha by 2. What is the, I mean, if you know what is z alpha, what is z alpha? Z alpha is the point after which the area is alpha. So then what is z alpha by 2? Z alpha by 2 is the area after which is the point after which the area is alpha by 2. So the area enclosed in this interval minus z alpha by 2 comma alpha by 2, the area enclosed is 1 minus alpha. So we understand. So probability of z being in this interval is 1 minus alpha. Fine. And okay, what is the context? We know the mean, we know the variance. Fine, that is the context. That is the context. Is there anything else? So, what is happening? Okay, we know if probability of z greater than z alpha is alpha because area is essentially the probability, right? So, area after z alpha is alpha. So, that is the probability. Probability of z being greater than z alpha is alpha. That is fine. And we just saw probability. How is it 1 minus alpha? Because alpha by 2 is the gray region, alpha by 2 is the gray region, that the sum is alpha. So the white region is nothing but 1 minus alpha, which is essentially what is written. So nice. uh, okay, probability of minus z alpha by 2. Okay, probability of z being in this interval is 1 minus alpha. Nice. uh, So Z is nothing but standard normal random. Yes, so standard normal random variable. I have one standard normal random variable with me, which is the first one, x bar minus mu by sigma by root n. This is one standard normal random variable. So what I can do is I can replace my capital Z with my new uh, representation. What am I replacing? Capital Z with x bar minus mu by sigma by root n. So divided by root n will come to the numerator because uh, that's it. See, you get it. It's simplification. Fine. Now we have a new representation. We rewrote the old one into this new thing. Now after some rearrangements, what you will get is you will get what will you get? What will you get? Okay, here, if you look at this last line, probability of x bar minus something something. So this is nothing but probability of mu lying in some interval is equal to 1 minus alpha. Probability of some mu. oh, not some mu, probability of mu lying in this interval is 1 minus alpha. So I have some interval and I'm stating that mu is going to lie in this interval. And the probability of that is 1 minus alpha. Mind you, we are still using capital letters. That means we're dealing with random variables. So there is probability. The moment you start substituting the uh, random variables with values, then there is no longer probability. It becomes confidence. So we'll see. So if I multiply 1 minus alpha with 100, I'll get the percentage, right? So here what is it in? Confidence interval for mu is this one. So what does it mean? It means with let's say alpha is 1, not 1. Let's say alpha is 0.1. If alpha is 0.1, what is this going to be? 1 minus 0.1 is 0.9, so 90%. Okay. If alpha is 0.1, then I can say that with 90% confidence that mu is going to lie in this interval. So what is the difference between capital X and small x? Small x means it's a value. So they will give you some data points. Just find the x mean, x sample mean. So just find the sample mean. You'll get some number. So some number minus uh, z alpha by 2. We can look at the table, right? We can look at the normal distribution table and get the values of z alpha by 2. Uh, n is nothing but the number of samples that you took. Sigma is a population parameter. So what is the context here? The context is when sigma is known but mu is unknown, right? Okay, no, no, no. Sigma, you want to find sigma, sorry, you want to find mu, but sigma is known. So with the help of sigma, you're finding what is mu. Finding in the sense, not exactly, but you're just finding an interval. You're like, mu is going to lie in this interval. What is the confidence? 100 into 1 minus alpha percentage. Here, this is the confidence after you substitute the values. Before you substitute the values, it is still a random variable. At that point, it is a probability. I think there is a separate slide explaining whatever I'm telling right now. You can go through it later. So, okay, more examples. Good for us. Good for us. Good for everyone. Okay, see, look here. There, they gave us sigma. That is fine. Sigma is known. Mu we want to estimate, so we want to find. Okay, 1 minute, 1 minute. Just 1 minute. Just 1 minute. Okay, fine. I think there will be more gaps in between because uh, I'll tell you later when I'm back. There are many things happening at this point. Okay, I was telling that sigma is given. We want to find an interval for an interval in which mu could probably lie. We know the interval. This is how the interval is going to look like. Fine, let me just go to the table. Where is the table? There is some magical table. Let me go to the table. Where is the table? Yes, so this is basically the summary of confidence intervals. Uh, you have some intervals, uh, confidence intervals. If you want to find where is mu and sigma is known, there is the confidence interval. You want to find where is mu but sigma is unknown, then you have confidence interval. You want to find where is sigma square but mu is unknown, you have a confidence interval. And this is where you find the t distribution and as well as chi-square distribution. That's why I wrote the previous thing here. These three things will help us later, but this table is a summary. So what is happening here is oh wait, why did I come back? The point is, if you know this table, you don't have to memorize it. So that's why I'm just going through things, so you don't have to actually memorize it. So all of them are like almost connected. So if you know one thing, you will know the other thing. So you don't have to break your heads. So here the confidence interval is this one. You have capital letter. So we know this. If you the thing is, if you want to find in which interval mu is, given that you know sigma square, you don't have to do anything. You just have to write mu will lie in this interval. But what is the confidence? Confidence will be 100 into 1 minus alpha. Uh, I told you. Okay, okay, okay. I'll tell you. So this is the confidence interval, right? I told that we're using capital letter here. So what does that mean? This is a variable. You did not substitute the sample data yet. So 1 minus alpha will be the probability of mu lying in this interval. The moment you substitute values, so what does it mean by substituting values? So capital X bar will become small x bar. That means you substituted the values. That time you wouldn't call it the probability. You will call it confidence. So in that case, 1 minus alpha is the confidence, or the percentage is 100 into 1 minus alpha. So that is the difference. Confidence is after substituting. Probability is before substituting values. It's like the estimator and estimate. Estimator is before you substitute the values. Estimate is after you substitute the values. It's just uh, it's just notation. Do I say notation or terminology? Yes, it's just terminology. But okay, fine. Where were we? We were there. We were there. Where were we? Yes. No. Yes. No. Yes. No. Yes. No. I think if you get the basic idea, it's fine. So I'll not go through many examples. But where was I? Oh yes, we were here somewhere. Yes. So here, if you see small x is there, so that means you already substituted the values. Even if you didn't substitute, it means you substituted the values. So you only call it confidence. You wouldn't call it probability. So if sigma is known and you want to estimate in which interval mu is there, you just uh, write this interval. Confidence is 1 minus alpha into 100. Simple. So if you know the confidence interval, you don't have to derive it anyways. You just have to write it down. So yes, so this slide is essentially trying to tell that why and all you can look into it later. They won't ask you why and all. That is fine. But interested people can look into it. Like why is there a difference in terminology? What does it actually mean when I say confidence is 90? So all of this is basically stating that you don't they wouldn't ask you. Okay, fine, beautiful. You can look into it later, or maybe. Okay, so if you notice the confidence interval, Uh, 1 minus alpha. See, if you try to increase the confidence, the interval length will also increase. The problem with that is see, if I say mu is lying from minus infinity to infinity, that is nice. With 100% confidence, I can say mu is lying in between minus infinity to infinity. But what is the point? It doesn't help you in any way. So that's the thing. So as your confidence level increases, the length will also increase. The opposite also is also true. You decrease the confidence interval length, but in that case, your confidence decreases. So you have to find the right balance. So this is one example. So 95% confidence, width is something. 99% confidence, width is it's a bit large. So the problem is now you wouldn't know like where is mu? Is it there, 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 or there? The smaller the interval, the better is the accuracy. But in that case, confidence will start falling. So yeah, so that is a trade-off. So you get it right. Precision. Okay, they're talking about precision. Fine. Less precision. Reliability. Reliability. Reliability is talking about it's like about confidence, and precision is about the length. So smaller the width, better the precision. Reliability is basically higher the confidence, higher the reliability. Fine. Examples, you can look at it. There is nothing for me to tell. Okay, okay, we have something. What is this called? Bound. And so it was like you can either take 96 or 97, that is fine. But if you mention the 96.04, that is fine. But you have to round it off because n can't be a decimal number. Uh, okay, so that confidence interval has a lower bound and an upper bound. So there is something else called a lower confidence interval and upper confidence interval. Uh, okay, so that is out of syllabus. So fine. In the table also, only first column is coming. Only two-sided confidence intervals. Fine. So we will not go through upper and lower confidence intervals. I was just checking the. So okay, fine. So upper confidence intervals and lower confidence intervals are out of syllabus because it is mentioned in the syllabus sheet. So we then our thing is done. So we don't have anything else to do. Oh wait, we have two other contexts, right? The other cases. What is this context? Normal. Yes. So this is the second context. What is the context here? Second case. Previously we had sigma. Now we don't have sigma. Sigma is unknown, but you still want to find the interval in which mu is lying. So we'll be using this one. uh, you can see it. Okay, we can't see it. We will be using the second random variable x bar minus mu by capital S by root n. It follows a student t distribution. I don't know why it is called student t, but it is called student t distribution with n minus 1 degree of freedom. So the idea is same. So we don't have to derive it. The idea is essentially same. The idea this is also a symmetric distribution. So uh, like normal distribution, standard normal distribution. This is also a symmetric distribution. So the same process you do, but instead of z now you have t, and instead of z alpha by 2 you have t alpha by 2 along with n minus 1 because you have to specify the degree of freedom as well. So finally, it looks like the previous confidence interval only, but what is different is Instead of z alpha by 2, you have t alpha by 2 n minus 1, t alpha by 2 comma n minus 1. This is just one number. And instead of sigma, you have s, because sigma is unknown in this case. Uh, See, here random variable is there. That's why we wrote probability of this, probability of mu lying in the interval is 1 minus alpha. The moment you substitute it, you say confidence. So mu lying in this interval with some confidence, 100 minus 1 minus alpha. Fine. So instead of z, you have t. That's it. Uh, Everything else is the same. You can upper and lower confidence out of syllabus. Upper and lower is not there for the exam. Questions. So this is, see, solution. This person is starting by writing the confidence interval only. So even you can do that. So if you know the confidence interval, like which confidence interval to use in which case, then you're good to go. And they should be giving the values like z alpha, t alpha, all these values they have to give. We won't be calculating them. So you can expect that the values, the required values will be given in the exam. Unlike in the tutorial, because in the tutorial, when we are solving it, we can always open the math folder and go to the table. In the math folder, we have all the distribution tables, so you can have a look at it. In the exam, they will most probably not give us the tables. They will give us the required values within the question itself. Like in minor, I think did we have z values in minor? I don't remember. I think we did. Okay. Anyways, there's a last. Uh, okay, they're just comparing. Uh, what is this telling? This is okay. They're telling that on an average, the first confidence interval that we looked at, where sigma is known, that confidence interval will be smaller. What do you mean by an interval being smaller? Interval being smaller means you have higher precision. When would you have higher precision? How would you get higher precision? If you have more information. In the first case, we know what is sigma. In the second case, we don't know what is sigma. That is why, on an average, the first confidence interval is shorter. That is fine. Very intuitive example. The thing with chi-square is, okay, before that, the third case is when you want to find an interval for sigma square, but mu is unknown. Then what do you do? There is a confidence interval for that as well. Okay, now, but the thing with chi-square distribution is it is not symmetric. But that doesn't change anything other than the confidence interval. So we have a new confidence interval. We don't have to go through the derivation. The idea is the same. It's like you have alpha by 2 after this, alpha by 2 after this. In the middle, you have in the middle, you have 1 minus alpha. Uh, yes, so we start with this. This is nice. So we know, like, not that we derived it, but we're just seeing, like, this is there. I think derivation and all will be at the end, somewhere in the appendix, probably. But we don't have to go through any of that. We don't have to go through any of that. Fine. So after some derivation, what will happen? We will reach our confidence interval, which looks like this. So it's easy to remember because here we have n minus 1 s square by sigma square. We just interchange chi square and sigma square. So something like that. So you'll get n minus 1 s square by chi square. That is how you could remember the confidence interval. N minus 1 s square by chi square. In the what is this called? It's not suffix. Uh, Basically, at the bottom, you'll get alpha by 2 comma n minus 1 because degree of freedom is n minus 1. And right side, careful, you have 1 minus alpha by 2. Careful. Unlike, okay, we'll go to the table. Maybe then we'll see. Table. Where's the table? Table. All examples you can go through. Yes, so table. So the lower interval, upper interval out of syllabus. So we will not go through that. Only this much is there. So left side x Left side may minus will come, the right side plus will come, so it's an interval. Here the only change is here instead of alpha by 2 you have 1 minus alpha by 2. That's it. Because it is not symmetric, no, so you will get some dissymmetry. That is why you have 1 minus alpha by 2. 1 minus, okay, fine. So done. Confidence interval is also done. So this means unit 5 is done. So I've told everything. I didn't expect that it would take a lot of time, but okay, fine. Now I will move to unit 4 in 1 minute. You can look at this table for a while. I will be here. Hmm. Okay, fine. I'll just go there. So confidence. Just look at the tutorial problems. You will understand how to solve them. Okay, 11, 12, 13 is done. So unit 4. What is in unit 4? Probability distribution. Oh my goodness, that. No, I said 5, 3, 4, right? What was the order that I told you people? 5, 3, 4. Okay, 5, 3, 4. So I'll begin from unit 3. Uh, unit 3, unit 3, unit 3. Probability distribution. Uh, okay, we'll go there. Probability distribution. Here. Oh, nice. It stopped at normal, but we will start from the beginning. We don't have a binomial and Poisson, but it doesn't mean. See, I think I was not there when Sir was talking about this, but what I was told was you won't get direct questions, but you can get indirect questions, isn't it? But okay, fine. I'll just skim through the things. Uh, will not explain anything. See, at this point, what are you supposed to know? You're supposed to know PMF, CDF, the relationship between them, uh, the mean, I mean, the expectation, mean expectation, the same thing, variance, at least these things. So PMF or CDF, whichever one is comfortable, whichever one you're comfortable with, and then expectation and variance. If you know, then you're good to go. And probably where to use which distribution. Sometimes you can use Poisson approximation, all those things are there, no? So sometimes binomial can be approximated using Poisson. Sometimes, not some, most of the times, this gamma is in. No? Gamma is a very complex looking function. We can solve gamma using Poisson. Like if you know, is it Poisson? Yes, I think yes, because exponential came from Poisson. Exponential is nothing but the waiting time between each occurrence in Poisson, and gamma is fine. See, I mean, we'll just see. We'll just go and see what is there. No, no English, please. Uh, Discrete. What is discrete? Bernoulli is discrete. Is it in the syllabus? It's not even there. So it's simple. Everyone knows. It's just we know. There's nothing to talk about in Bernoulli. See, it's simple. It's very simple. There's nothing to talk about in Bernoulli. See, it's absolutely very simple. Just have two possibilities, 0 or 1. There's just one trial that you do in this, one Bernoulli trial. So its expectation is P, its variance is P into 1 minus P. Nice. Binomial is nothing but a collection of Bernoulli. That's it. Given that they're independent. Okay, so this is the first time the word independent and identically comes into picture. So IIDs. This is the first place I think, but we did not realize it's just independent and identical. But then it came much later into the picture. Fine. So binomial is basically some n Bernoullis. So its expectation is NP, Bernoulli expectation is P. So binomial expectation is NP. Variance is N into P into 1 minus P. They wouldn't ask direct questions though. This is nothing but like combinations. You know how to write this. This is fine. This is fine. So N is the number of trials, K is the number of successes. So success, probability of success power K, probability of failure minus number of failures. Fine, that is Bernoulli, binomial. Nice. So there is nothing to see. Expectation NP, variance is NP 1 minus P. Fine, that is also fine. Okay, alternative way is using MGF, but then MGF is out of syllabus. Uh, so you don't have to break your head probably. There's so many things that have been cut off from the syllabus. Uh, okay, let's see. Uh, See, in Unit 1, they're like PMF, PDF, CDF, all of this is cut from the syllabus, but somewhere, somehow, we are still using PMFs and PDFs, right? Later on. It's just that they won't ask you direct questions. So we will also not pay direct attention to it. So fine, MGF out of the question. Okay, fine, too many examples. Too many examples. Example, fine, beautiful. Nice. Go on. Okay, nice. Example. Yeah, I don't think you have to. Is skewness kurtosis in the. No, moments are out of syllabus, so I don't think they will ask you skewness and kurtosis. At least for binomial and Poisson, I think. I would be very much surprised that if they ask about skewness, they won't ask. I don't think so. Okay. I mean, mean is we know every. I think everyone knows at this point. Mean, variance, other things not required. I don't think other things are required. Binomial PM. We know binomial PMF. P bar X. Oh, okay. Binomial. Okay, fine. We have to take the use combinations. No? So this is like as n increases, it's trying to take the shape of something. So that is the basic idea of central limit theorem, which we'll come to later at the end of this 134 slide PPT. Sum of binomial is also binomial, right? Yes, sum of binomial is also binomial, but its first parameter changes. It becomes n1 plus n2. Fine. Okay, more examples, more questions. Okay, exercise. Okay, more exercises. Okay, now this is also deleted from the syllabus, but it doesn't mean you will not use it, right? So we'll just see what is in Poisson. Uh, this is also discrete. It will tell us in a given number of, okay, let's say there is some fixed interval of time, some number of events are happening. Fine. It will give you the number of events occurring in a fixed interval of time. So the parameter lambda is the mean as well as the variance. So that is also fine. In a unit interval. Okay, so x is defined to be the number of occurrences in a unit interval. Okay, then lambda represents the rate, I think. So the rate at which something happened. Okay, fine. Go on. Where is the PMF? Okay, so here we got our PMF. So nice. So this also, I don't think that you need to specially remember this. Most of you would have already known that this is Poisson. They won't ask you direct questions, so we don't have to bother much. But I don't know. See, you people must have been in class. Recall whatever Sir said because I was not in class when Sir was discussing about the syllabus. So whatever Sir said, just keep that in mind. Don't take my word because I was not in class when Sir was discussing about the deleted portion. I was not in class. But anyways, this is a Poisson distribution. Mean is lambda, variance is also lambda. So beautiful, amazing. We will not look at MGF. We will absolutely not look at MGF because MGF is out of syllabus and they have other good questions to ask than about MGF. Uh, okay, so that was unit interval. If the interval is uh, okay, unit interval means length is t, no, length is 1. So here they're talking about an interval with length t. So what changes? Lambda changes. That's it. So instead of lambda, you'll have lambda t. That's it. Generally, t is 1, but t could change. Or else you can replace lambda t with lambda prime or some other thing. A new rate now. So lambda t is the new rate. So fine. So what is rate? Rate is basically number of occurrences per unit time. That is the rate. And what does the length of the interval represent? It represents time. So fine, I'll move on. There's nothing much here. Fine. Okay. So lambda is the number of occurrences per unit time, but lambda t is the number of occurrences uh, per t time. T time in the sense an interval of length t. Fine. Anyways, Poisson is not even in syllabus, so we will not spend much time here. We know mean is lambda, variance is also lambda, so that I think that information is fine. Poisson approximation. Poisson approximation is when, let's say, you have some binomial distribution. When n is very large, like n is greater than p, basically when n is a very large number compared to p, then you can approximate binomial to Poisson. So that is Poisson approximation. So instead of using binomial, which is here down, we can use Poisson approximation. But binomial, we have n and p. Then in Poisson, we only have lambda. So what is this approximate value of lambda? Approximate value of lambda is nothing but np, because lambda is the mean, and in binomial, np is the mean. So lambda is equal to np in Poisson approximation. Fine, I'm just giving you the brief idea. That's it. Binomial can be solved using Poisson when n is a large number compared to p. In that case, lambda is going to be np. That is how you do Poisson approximation. Uh, okay, so adding Poisson variables will also give you a Poisson variable. The new parameter is basically the sum of all the original parameters. So sum of all lambdas. Okay, but difference is not a Poisson. Okay, fine. Too much information. Poisson is not even in syllabus. Let's go on. Wait, what? This is what was this again? Are they independent? Okay, independent. So yes, okay, independent. Independent is one thing to keep in mind. Sum of independent Poisson variables. So sum of independent Poisson variables is fine. So we will not look at. Okay, they're doing MGF. No, we will not look at MGF. MGF is not a concept. Fine. So mean is lambda, variance is lambda. I don't think we need to know anything else more than that. Mm, because what is skewness and kurtosis comes under moments, right? And in unit one, it looks like it has been deleted. So we'll not look into that. Okay, fast. We'll have to go finish this. Uh, we have to finish this probability distributions soon. Uh, okay, so if lambda increases, I think it's going to. So okay, same story. This is like foreshadowing at this point. Uh, as lambda increases in Poisson, as n increases in binomial, the graph, the plot tends to a certain kind of distribution, which we'll look at in central limit theorem later. Fine, exercises. Uh, okay, discrete is done. Discrete is done. Okay, so they've completely deleted the discrete probability distributions. How nice of them. Okay, continuous. First thing, uniform. Okay, okay. Where is uniform? Okay, uniform is here. This is in the syllabus, so maybe just just careful. I think it's nothing to be careful about because uniform is the simplest of all the probability distributions, isn't it? So you have an interval A to B. PDF can be found simple 1 by B minus A, very simple. And yes, don't forget to write 0 as well. Don't simply write 1 minus 1 by B minus A and smile to yourself. Also write PDF is 0 when x is outside this interval. That also you have to write. You can't simply say PDF is 1 by B minus A. No, it's up to sir. If sir is happy, he might not penalize you for that. But if sir is not happy, then maybe I don't know. Up to you. But this is how you write it. So you should write 0 also. 0 when x is outside the interval. Outside the interval is x is less than a, x is greater than b. CDF. See, they told CDF is out of syllabus, but it doesn't mean uh, you will have to stop using PDFs, PMFs, and CMFs. So this will keep coming probably, but you won't get direct questions uh, from Unit 1. But this is not Unit 1. We are in Unit 3, and uniform distribution is very much in the syllabus. So this is CDF. What is relationship between CDF and PDF? If you if you differentiate your CDF, you'll get your PDF. I think everyone should have I think everyone knows that at this point of time. Fine, fine. Maybe when they said CDF and all is out of syllabus, I think you won't get questions like verify if this is uh, check if this is a CDF or not. Like we had some properties. No, I don't think they will be asking those kind of questions because I think they are already covered in the minors. So majors you will get some other questions probably. Uh, Uniform. Okay, these are the graphs, right? CDF looks like this. PDF looks like this. Fine, nice. Okay, expected value. So expected value is nothing but a plus b by 2. Variance is b minus a square by 12. If you want to sit and derive in the exam hall, you can do that, or else you could do yourself a favor by just remembering these two values. Mean is very much understandable, right? Mean is or expected values just the average a plus b by 2. That is easy. B minus a whole square by 12. That also seems simple. You might wonder from where did this 12 come? It just came, so we can't help it. Maths is telling us there is a 12 in the denominator. Fine, mean variance, uniform distribution. I think we are done with it. We will not look at MGF. So, I mean, to be on the very safe side, just know how to find MGF. But I don't think they'll be asking us. I don't think any question will come related to MGF. But don't take my word because they said uniform distribution is in syllabus, but then they're like MGF is out of syllabus. So we'll not pay much attention to this. See, only 5 questions are coming. You expect there to be a question on MGF? I don't think so. Uh, Friends arrival time. Okay, this I think we are going to the other distribution, exponential distribution. Where are you? Oh, there are some nice ideas here, but like how are we going from Poisson to exponential? Like in a nice story kind of way they explained in the slides, but we'll just go on. We'll not read stories now. Wait, what? Where is it? Did we cross it? No, I don't think so. Oh, it's still poison. Okay, it's still poison. Fine. We will go to expectation. What is this? Exponential soon. We're still in poison. Sorry, no, this is uniform, right? Fine, fine, fine. My bad. We are in uniform. So mean is a plus b by 2, variance is b minus a square by 12. Uh, okay, interesting. The skewness is 0. That is interesting. So maybe even coefficient of kurtosis. So I don't think it would hurt to remember that 0 and 1.8 is there. Like it's just a number, so I think it's fine. Do you guys even remember what skewness and kurtosis is? Like skewness, fine. We'll not get into that. You can just kurtosis is basically the height thing. Like how high is it? Skewness is basically like it's skewed to the left or skewed to the right. The tail, if skewed to the left means the tail is on the left side. Skewed to the right means tail is on the right side. Fine. Anyways, we'll not look at MGF. Exercises. Okay, exercises. Okay, okay, fine. So we've come to exponential distribution. Okay, fine. I just 1 minute. Let's see if this. Just 1 minute. Just 1 minute. 2 minutes. Sorry, 2 minutes. One more minute, please. Just 1 minute. One more minute, please. Just 1 minute. Okay, that seems to have. I think that should be enough of a break. Okay, it seems it seems that I've taken a long break. Fine, got some news. Anyways, expo. Okay, wait. Okay, exponential distribution. Okay, exponential distribution. Fine. Uh, if you remember what Poisson distribution was about, you have there's some time interval. In the time interval, some things are happening. So some occurrences are happening. So exponential distribution basically, we'll see. It's like it should be written somewhere. Okay, okay. So now we will see where how is exponential related to Poisson. Now we just defined a new random variable called waiting time, and waiting time is uh, continuous because time is continuous. Okay, so the idea is uh, what does CDF mean? CDF means probability up until that point. So P of x greater less than or equal to small x 1 minus. Okay, fine. What does P of capital X greater than small x mean? It means waiting time is more than small x. What do you mean by waiting time is more than small x? Uh, what are you waiting for exactly? You're waiting for the occurrence. So when you say waiting time is greater than small x, it means from time 0 to time small x, no occurrence happened. That is why this is nothing but no occurrences in the interval 0 to small x. And what do I mean by no occurrences in 0 to small x? What is the probability that in the interval 0 to small x, nothing happened, no occurrences? Now, if you remember, now we can bring the Poisson uh, uh, into the picture, Poisson distribution. Because what is Poisson distribution? There is some interval, there's some time interval. In that, uh, let's say you have X occurrences, then you have the PMF for that. But in this case, no occurrences. So zero occurrences in this interval. So what is it going to be? If you remember the PMF of Poisson, it's uh, you substitute. Do I write it? No, I don't have to write it. If you know how to use Poisson, you can just substitute. You will get e power minus lambda x, because in Poisson, when the interval was of length t, we got lambda t. Here our interval is of length x, so we'll get lambda x. So number of occurrences is zero, so we'll get e power minus lambda x into uh, lambda x power 0 by 0 factorial, because 0 occurrences, right? 0 factorial is 1, all of that. Fine. So finally, this is the CDF of the waiting time. And waiting time, so what does this even mean? So uh, waiting time is less than small x. So that is the CDF, right? Yes, so waiting time is less than small x. So P of capital X greater than small x is waiting time being greater than small x, which is nothing but no occurrences in the interval of 0 to x. So that is how Poisson and what is this? Which exponential are related. So after in 0 to x, no occurrence means we are waiting for the first occurrence, right? So like after x time has passed, some maybe the first occurrence is going to happen. So that is fine. So if we have CDF, we can find PDF. So this is the PDF of exponential. Uh, Fine, this is fine. So here, what does X represent? X is the time. So time is like from 0 to infinity, right? So before that, it's 0. That is fine. No, we will not look at moment generating function. Okay, but we need these values. So expectation is 1 by lambda, and variance is 1 by lambda square. Yes, so 1 by lambda square. Lambda is the parameter of exponential distribution. If you notice, how did I write the CDF of exponential distribution? I simply used Poisson, so I didn't have to memorize anything new for exponential. I just used some logic for exponential. Like I used the PMF of Poisson distribution while trying to write the CDF of exponential. The no occurrences in 0 to x interval. There I used the PMF of uh, Poisson. Anyways, memoryless property. Okay, fine. Is this okay? Fine. So since exponential is a part of the syllabus, memoryless distribution. It's like let's say you have a car and you're using the car. So you would feel that if you keep using the car, it's maybe its life is going to deteriorate or something. So let's say you buy a new car and you drive it for 5 hours. You would think that it's, or let's say 5 years. Let's say 5 years. You drove a car for 5 years. You would think that at this point of time the car must have lost its something. Maybe I don't know. Like it's old now, like kind of old. So it won't have its original power as before, or something like that. So you would expect that now if you start driving, like it might uh, it might reach a breakdown at a higher probability. When you buy the car, there is a very less probability that it's going to break down in the next few hours or something. But if it's like 10 years old, 15 years old, it's very high chance of breakdown. But the problem is exponential distribution does not consider that. So what does it say? You drive the car when you purchase it, or After 10 years of purchasing it, it doesn't matter. The probability of there being a breakdown, it's like it's going to be the same. There'd be no change. So that property is called memoryless. It doesn't matter when you purchase the car or whatever. It will give you the same answer. So uh, now this is a nice explanation. So you can read the scenarios here, so you will get what I'm talking about. The memoryless property. Okay, wearing down. Yes, so that was what I was searching for. Wearing down. Yes. So if there's any phenomenon where wearing down happens, wearing off happens, you wouldn't probably choose exponential distribution because it has a memoryless property, so that is not going to give you uh, nice prediction as to when it's going to break down or whatever. So here breakdown is like the occurrence. When is the breakdown going to happen? Okay, you can go through this. It's like uh, what is capital X? Capital X is like uh, let's think of it as time. So capital X is time. So probability of capital X being greater than S plus T. So S is like until let's say years. So S is the number of years that you've drove until now, and T is no, T is the number of years that you've drove until now, and S is the number of years for which you're going to drive more, something like that. So probability of X greater than S plus T, given X is already greater than T. So given that you've drove the car for T years or something, what is the probability that it will go for like more S years more? So how do you say that X is greater than S plus T? That is fine. Memoryless property says that this is equal to probability of X greater than S. So it doesn't matter. It doesn't matter how many years, for how many years you've drove the car or something. So that greater than T just, it doesn't matter. That information is pointless because exponential distribution is memoryless. So like how do you write P of X given by, or P of A given B? It is nothing but P of A intersection B divided by P of B. So that is what is here in the second point. And okay, nothing much is happening here, is it? Nothing much is happening. Nothing much. So they're just rewriting the same thing. Nothing much is happening. Fine. So if you read the scenarios in the previous slide, maybe you'll get an idea as to what is memoryless. Anyways, moving on. We'll have to speed up, speed up, speed up, speed up. Exponential is fine. It has some memoryless property. So yes, so for exponential, so uh, if you have a p of x greater than something, it's like the waiting time problem only. So you can directly write this is e power minus uh, lambda. How much? E power minus lambda x. Yes, so here x is 600. So e power minus uh, 600 lambda, 600 lambda. Where lambda? What is lambda here? Is there a lambda in the first place? Okay, lambda is 500. Fine, nice. Oh no, wait, no. Mean is 500. 1 by lambda is 500. So lambda is 1 by 500. Yes, careful. This is not Poisson. In Poisson, mean is lambda. Exponential mean is 1 by lambda. Careful, careful, careful. So how is this related to Poisson? It's like from 0 to 600, no occurrences. So you will get, uh, what do you get? If you see, this is essentially Poisson. This is how we derived the CDF for exponential, right, from Poisson. So If you want to remember, you can remember, or else you can just know, like, if you know how to use poison in this, that is fine. This kind of a procedure will be helpful in gamma. We'll come to gamma once. So gamma is the next thing, right? So we'll see. Okay. So yes, so exponential distribution may not be the best model. Yes, fine. Because it does not consider the wearing out, the wearing of property of objects. Gamma distribution. So gamma distribution is like a more generalized form of exponential distribution. So yes, so this is the first line. I was talking about the first line. So what is an example of an exponential distribution? An example is the waiting time uh, between the occurrences of poison distribution, because poison distribution is basically uh, like occurrences per unit time, right? So if there's any random variable representing the number of occurrences per unit time, that follows a Poisson distribution. So the waiting time between occurrences, if that is a random variable, then that random variable will follow exponential. But what kind of waiting time? That waiting time is waiting time until the first occurrence. That is exponential. So here waiting time until the alpha occurrence. That is gamma distribution. So gamma distribution is a generalization of exponential distribution. So we will use Poisson again to write down the PDF or PDF no CDF of gamma. So what is f of x? F of x is basically p of x less than or equal to fine. So now again I'll ask you what is p of capital X greater than x? If you want to find okay, what is capital X at this one? Capital X is the waiting time until alpha occurrence. Capital X is waiting time until alpha occurrence. When I say capital X is greater than small x, it means waiting time until alpha occurrence is more than small x. So what do I mean by waiting time is more than something? So it means in the interval 0 to small x, less than alpha occurrences have happened. So what do I mean by less than alpha? Because after this time only the alpha occurrence will happen. Before that, in the interval 0 to x, less than alpha occurrences have happened. What do I mean by less than alpha? Alpha minus 1, at most alpha minus 1, right? So now I'll use Poisson. So my interval length is x. So how does Poisson look like? It looks like lambda t power number of occurrences. You remember, right? So here, let's say k is the number of occurrences. So at most alpha minus 1 means you could have 0 occurrences, 1 occurrence, 2 occurrence, 3 occurrence, so on until alpha minus 1 occurrences. That's why there is a summation. Uh, that's it. Length of the interval is x. So you have lambda x power number of occurrences, e power minus uh, lambda into length of the interval divided by number of occurrences factorial. This is basically Poisson distribution. So if you simply have p of capital X greater than x, like if x is a gamma distribution random variable, if you simply have p of capital X greater than small x, you can directly use Poisson. You don't have to touch the PMF or CDF of PDF or CDF of gamma. Without even touching that, we can uh, solve gamma using Poisson. In the tutorials, I think I used this process somewhere in some question. I think wherever gamma appeared, I used this only. I somehow used Poisson itself. I did not use gamma PMF. But it doesn't mean that you shouldn't know how does the PDF and CDF of gamma looks like, right? Gamma distribution. So we'll look at it. This is CDF. Fine. CDF is fine. So if you simplify in the sense, if you try to find the PDF, you get something. This is the PDF of gamma. They did not simplify the CDF, they just left it in terms of summation, but that's fine. Okay, nice. This is PDF of gamma. So alpha is like the at which occurrence? Alpha occurrence. Lambda is like from it comes from the poison thing. Lambda comes from poison. So exponential is simply uh, only it only has lambda as its parameter, but in gamma you have alpha and lambda because alpha is like which occurrence until alpha occurrence. Fine. In the denominator, alpha minus 1 factorial has been replaced with the gamma function because factorials are not defined for decimals. So gamma of alpha is nothing but alpha minus 1 factorial for integers. Since gamma is continuous, you have to account for decimals as well. So there is something called a gamma function. Uh, this is PDF. So if alpha is 1, basically if you're waiting until the first occurrence, that means it's exponential at this point. So if you put alpha as 1, you'll get exponential. Okay, gamma is also fine. Now we have to rush to. Okay, fine. What is the mean and variance? Mean is alpha by lambda. Variance is alpha by lambda square. Uh, no, we don't have to check validity, I suppose. Okay, nice, beautiful graphs. Okay, mean is alpha by lambda. Variance is alpha by lambda square, right? Yes, alpha by lambda square. Fine. MGF we don't have to look at it. Uh, example. Okay, fine. Just want to go down. Is there anything? No, I don't think so. Chi-square. So chi-square comes from. Is it in the syllabus though? Let me see. Uh, there is no special mention, but this is a part of gamma itself. There's nothing that you're supposed to do. In gamma distribution, replace lambda with 1 by 2 and alpha with r by 2. That's it. R is called the degrees of freedom. That's it. So in your gamma, if you replace lambda with 1 by 2 and alpha with r by 2, you get your chi-square distribution. So if you do that, what will happen? Now your mean becomes r and variance becomes 2r. I mean, see, alpha by lambda square. This substitute, you will get alpha by lambda and alpha by lambda square. You just substitute, you'll get r and 2r. Mean and variance, r and 2r. Fine. We will not look at MGF. I'll be doomed if they ask an MGF question, but they shouldn't ask. They've nicely uh, cut it in the syllabus sheet, didn't they? Okay. Okay, nice. So gamma is also done. We have normal distribution. What is a normal distribution? Nice. Okay, nice. Normal is normal. Very normal. Okay, normal or Gaussian? You have two names. Okay, so this is the PDF of normal distribution. I think uh, it's not zero anywhere. It's like it's just there. So only at infinity it's zero, but then at, at finite places nowhere it's zero. It's like it's a symmetric curve. You can see. So mean is at mu, and standard deviation is sigma. Everything is there. So mean is mu. The standard deviation is sigma. Variance is sigma square. That is also okay. See, sigma is greater than 0 because if sigma is not greater than 0, sigma can't be negative as well. So then sigma has to be 0. Then if sigma is 0, what does it mean? Standard deviation is zero. What do you mean by standard deviation is zero? It means all the points are at mu, and that is very rare. That wouldn't happen, right? All the points wouldn't be at the same place, because if you collect samples, you'll okay, fine. We'll not get into that. So sigma is usually just greater than zero, because sigma is standard deviation. There'll be some deviation. It's not that all the points will coincide at mu. That even that will give mean as mu, but that's strange. You wouldn't usually get that. Okay. Okay, there's some properties. So gamma of 1 by 2 is root pi, apparently. Uh, will that be helpful? I don't know. But fine. Gamma of 1 by 2 is root pi. And okay, so this is a gamma function. Where is gamma function? Gamma, gamma. You can look up how does a gamma function. It's like an integral, 0 to infinity. I think 0 to infinity u power minus y e power minus u du. So instead of half, you have something, maybe alpha, then you get gamma of alpha, something like that. So 0 power inf here. Oh, I can copy this. No, I can't find. No, we'll not look at MGFs. Oh, yes. So we know after looking at the PDF of normal distribution, we know that expectation is mu and variance is sigma square. You can verify that as well. Mu sigma squared standard deviation. Okay. So since it's normal, it will have no skewness. It's like symmetrically distributed about mu. Kurtosis is 3. Does anyone remember the numbers for I remember the number. Okay, uniform distribution, right? Uniform distribution. Uh, I think coefficient of skewness was 0 there, and kurtosis was 1.8. I don't know if it's for uniform or not. I don't think it matters, right? I don't think it matters. But it's there. It just exists. No, uniform. 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 Mean was a plus b by 2. Variance was b minus a whole square by 12. Yes, and I think okay, yes. So I think skewness was 0 there, and the kurtosis was 1.8. I don't think skewness and kurtosis should matter, but at least normal. Skewness is 0, kurtosis is 3. Fine. MGF we won't look at it. This is how normal distribution looks like. About the mu, the graph is there, a peaked graph. Okay, now they're changing kurtosis. So the second graph kurtosis is. Are they changing kurtosis though? No, no. I think they're changing sigma. Fine, because kurtosis is constant. It's 3. Skewness is 0. Okay, nice, nice graphs. Fine. Theorems. If x is normal, some linear transformation of x will also be normal. Fine, and its new mean will be. You apply the same linear transformation. Fine. I mean, you can use expectation. So you can write x. You can find the expectation of y and the variance of y using the properties that we know about expectation and variance. You don't have to use the MGF. Change of origin will not affect the variance. So variance of y is equal to variance of ax. So constant will get squared. So a square variance of x. Variance of x is sigma square. That's why you have a square sigma square. Fine. That is also simple. You can do. Uh, yes. So if x is normal, then x minus mu by sigma is standard normal. This is what we were talking about uh, for some time, like previously, long ago. So standard normal means mean is 0, variance is 1. The standard Gaussian, whatever it is. So in the original PDF of normal, you just replace mu with 0 and sigma with 1. You will get something that looks like this. And phi of z represents the CDF of a standard normal random variable. So this notation at this point. PDF, CDF, fine. We'll not look at it. Okay, some properties. Phi of minus z is 1 minus phi z. You can always draw the graph, and since it's symmetric, no, so you will get some advantage like this. You can you don't have to memorize or something. You can just check what is phi of minus z. So here the property is p of z less than or equal to minus z is equal to p of z greater than or equal to z, because symmetry, it's just properties now. You can draw the graph and see for yourself. So what is happening here is you subtract x, you subtract u from x and divide by sigma, and you have to do for a and b as well. So you get a minus mu by sigma, b minus mu by sigma. Now you just have to take the differences of you just have to take the difference between the CDFs. So phi of b minus mu by sigma minus phi of, if you put it on paper, I mean it's right below the proof. So all of this is this doable, very much doable. So like there is some interval, right? Like they gave some interval mu minus sigma, mu plus sigma, and they gave some numbers 0.68, 0.95, 0.99. So it's like the probability that your random variable lies in this interval. Like in case you sample it, like what's the probability it's going to lie in this interval? So if you go three standard deviations away from the mean, so 99.73%, your x is going to lie in the interval. If you move three standard deviations away from the mean, is there a graph for that? Okay, so that is one standard deviation. Oh, they didn't. You get my point, right? So this is moving one standard deviation away, two standard deviations, three standard deviations. Like 99.9% area is here. Anyways, okay, fine, nothing. Pizza delivery. Okay, pizza delivery. Pizza delivery. One standard deviation, two standard deviation, three standard deviation. Okay, fine. Linear combination of independent normal variates is also normal. Okay, so if I add independent normal variables, what will I get? The new mean is going to be okay. I mean, they even multiplied it with they multiplied each random variable with some constant AI. So, okay, new mean is basically summation of AI and mu I. That is fine, and variance as well, because uh, there's this property for variance. No, if all xi's are independent, if all xi's are independent, then variance of x1 and so on till xn is equal to summation of variance of xi given x1 and xn are independent. If they're not independent, then the covariance thing comes into picture. What Was I here? No. Yes. Okay, I was here. Fine. So, or else when in doubt, simply apply expectation, simply apply variance. You can find on y expectation of y, you'll get mean. Expect variance of y, you'll get variance. It's easy to find than memorizing. So okay, fine. So x1 plus x2, x1 minus x2, they're all normal. So what will happen? See, here minus is there, but here minus won't come. So careful. Variance variance is sigma square, so you won't get minus there. Uh, mm, okay, so this is our sample mean, right? If you see, we're coming backwards, so this is sample mean. So sample mean is here. Fine, sample mean is there. If their IID is independent and identically distributed, then this will directly become mu. That will become sigma square by n. Which okay, fine. So okay, that was the next slide. Anyways, nice. So if that IID is, then mu I is equal to mu one equal to mu two equal to mu three. All that will happen. So at the end, you'll get mu and sigma square by n. And this is our nice little random variable, which is a standard normal random variable. Okay, nice. 100th percentile. So let's say you are at like you have something, let's say 99 percentile. It means 99% of the population is behind you or under you or something like that. So if your height is like, okay, in the given example 80th percentile, it means 80% of the population is smaller than you. Fine. So probability of x less than or equal to xp is p. So 80th percentile means x80. The point, that point is called 80th percentile. How do you ensure this is true? So probability of x before that point should be 80%. So simple. So xp is the point, p is the area. How much? Probability basically. Mm. So to the left of xp, you should have 80%. Only then x80 is called the 80th percentile. How do you get 80? You just have to do 100 into p. That's it. P is 0.8. So 100 into 0.8 will give you 80. Is there anything else? Okay. How do you find median in these cases? This is a continuous distribution. How do you find median? From, let's say we are talking about normal distribution. Uh, uh, okay, I mean normal in standard normal mean, median, mode. It's the same thing, mu. But if you're talking about some, let's say some continuous distribution, uh, it's like you start from the left side and go up. Like let's say you have PDF, you integrate the PDF from the leftmost point till the median. If you integrate, then your probability should be 50%. I think we had a question similar to this in the tutorials. Maybe if you see that, uh, like, I mean, I just, some question just came into my mind, so I'm just sharing. Nothing special about that question. Anyways, uh, okay, this is alpha. I mean, Z score, yes, so Z score. So many people, I mean, I met so many people who were confused about Z score. So many in the sense, just two people. So I'm still sane. I did not meet more people who were confused about Z score. See, we saw XP. XP is fine now. This is Z alpha. Z alpha is like the opposite. After Z alpha, there is some, okay, fine. Is there a graph here? I don't want to draw. Is there a graph? My goodness, there is a graph. Nice. So what is this telling? There is some Z alpha. What does it say? Z alpha is a point on the axis, the what do I call it? The Z axis. Upwards is probability, that is different. Down is the Z axis. So Z alpha is a point on the Z axis. After this point, the area under the curve is alpha. So such a point is Z alpha. That's it. So probability of Z greater than Z alpha is alpha. In other words, probability of Z less than Z alpha is 1 minus alpha. That is fine. So Z alpha is Z alpha. I mean, shouldn't be confusing. So what will the CDF of Z alpha be? CDF is basically probability of Z less than Z alpha. So that would mean 1 minus alpha. So CDF of Z alpha is 1 minus alpha. Oh yes, so it is here. See, CDF of Z alpha is 1 minus alpha. Nice. When in doubt, just draw the graph and see where is alpha, where is Z alpha, where is 1 minus alpha, where is all this happening. You don't have to memorize. Just draw this graph. So what can you see? Probability of Z greater than Z alpha is alpha. Done. You just have to draw the graph and write it. You don't have to memorize anything. Apart from the graph, though, you know how to draw the graph. Mm, okay, probability of Z greater than Z is 0. So this is alpha, so alpha is there. Fine. So we'll have to use the tables. They will either give us the tables or the values directly, whichever one is required. But we are supposed to know. They could give us like the properties in the sense, for example, uh, look at this. So Z, so this is one probability. This is one property. Z1 minus alpha is minus Z alpha. Why is that the case? Uh, See, when in doubt, just use the graph. So okay, 1 minute, 1 minute, 1 minute. Just okay, 2 minutes. Just one more minute. Okay, it's okay. I was talking about am I, okay. I was talking about the properties, no? This draw. Uh, we wanted to see, no, how is this equal to this. So let's say I have Z alpha here, then I will have minus Z alpha here because by symmetry, right? So what is this going to be? The area here is going to be alpha. The area here is also going to be alpha. What else? So what is Z1 minus alpha? Z1 minus alpha means After z1 minus alpha, the area is 1 minus alpha. Now time for some magic probably. So what is, if the area before minus z alpha is alpha, what is the area after minus z alpha? If alpha is here, then minus 1 minus alpha will be here. But if you notice, uh, so p of z greater than equal to doesn't matter because it's a continuous distribution, minus z alpha turns out to be 1 minus alpha. But we also know that p of z greater than or equal to z1 minus alpha, by using the z score property, I can write this as 1 minus alpha. This would mean minus z alpha is equal to z1 minus alpha. So something like that. Or else you don't even have to go into the equations. You just think. You don't have to, okay, let me just keep this here. You don't have to think. Uh, you don't have to write the equation. So after minus z alpha, you have 1 minus alpha. So this is nothing but z1 minus alpha. So that is how we write z1 minus alpha is minus z alpha. So these are some small properties. That's it. So it will be like, not that you have to memorize them. Like you will just probably use them in your uh, solution, because sir might not directly give. Maybe if you saw the tutorials, you'll probably see like you have to tweak a bit. How do I use the given information to get the information that I require to solve the solution? So okay, let's see if anyone messages. Okay, no messages. Mm, let's go. Fine, fine. All of this is fine. Example, fine. We're not problems, solutions. Yes. Okay. Okay. So gamma. Okay. Fine. Gamma function is here. Gamma function is here. I mean, it's not that they'll ask you to direct. They won't directly give questions on gamma functions. Gamma distribution is a different thing. It's just that it got its name probably because the gamma function is in the denominator of the PDF of gamma distribution. Uh, some properties, that's it, some properties. Okay, they gave some recursive relation, right? Gamma of alpha plus 1 is alpha into gamma alpha. Nice. This is some recursive relation. Fine. And what is the other thing I told you? Gamma of 1 by 2 is root pi. So that is also interesting. So I'll just keep that in mind. Mm, gamma of 1 is 1. Okay. And gamma of n plus 1 is n factorial. If it's an integer, that is yes. Uh, so, okay, fine. Here also. Gamma of 1 by 2 is root pi. Interesting. So, what was the other thing after probability distributions? Central limit theorem. Okay. No, this one, and I think I will do 9 as well, and then oh, 10 is also there. Okay. Let's increase the speed. Speed. Limit theorems. What is this? Okay, okay, fine. Central limit theorem is somewhere. I will directly go to. Oh, I can. Oh, this is maths PDF, right? I can skip to. Let's see what is here. Nice, interesting. Nice PDF. But we don't have this. This is out of the syllabus. Go down, go down, go down, 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 down. I just went there because I thought maybe something will be there between this and the other topic. But let's see. No, there's nothing new in between. I I don't see. I mean, why is this even here? What? Okay, let's see. What is it saying? Okay, so you have some IIDs and then they have finite mean. Then okay, this is some weak law of large numbers. Okay, fine. So this is like some estimator. Okay, this reminds me of no, the consistency will come when n is tending to infinity. Here n is okay, fine. N is tending to infinity. Fine. So this is very similar to the uh, what was it called? Consistency. Was it consistent? Yes, consistency. Very similar. I think it's the same thing though. I think it's the same thing. It is the same thing. This is the definition for consistency. So consistency is first appearance is in this slide. Is this other, but we didn't know it was consistency. But anyways, I don't think we should pay much attention to this. We have to go to central limit theorem. I want central limit theorem because in the syllabus they were like central limit theorem. So I will go to central limit theorem. I think for proving central limit theorem, you need all these things, but we are not going to prove anything, are we? Uh, at least the theorems. We might have some proof question, but I don't think to prove. Okay, let's see. You have some IIDs. You have some mean. They have some mean. They have some variance. For a large n, the distribution of x1 plus x2 and so on is approximately normal with mean n mu and variance n lambda square. Mean is n mu because if you take expectation of y, you will get expectation of x1 plus expectation of x2. All of that is mu, so you'll get n mu. Variance also, you'll get variance of x1 plus variance of x2 and so on. So you'll get n sigma square. That is also fine. Mm. Okay, so I can rewrite this. I can divide the numerator and denominator with something n. I think I can. Yes, I can divide it by n. So I will get back my. I think we'll come to that. We'll see. So yes, so I was talking about this. So if you divide the numerator and denominator, you'll get back the same thing. We've seen this. X bar minus mu by sigma by root n is standard normal. When was this the case? When x was a normal, when x belonged to normal distribution. But what is central limit theorem saying? Central limit theorem doesn't know from which distribution is x coming from, but we know that all of these x's are coming from the same distribution, but we don't know which distribution. But do we know anything about the distribution? We know that mean is mu, variance is sigma square. So central limit theorem is telling that as n tends to infinity, or for large n value, x1 plus x2 plus basically this whatever this random variable is, this tends to a normal. Uh, this random variable, the probability distribution tends to a normal distribution. Uh, I mean, we've seen, no, initially for binomial, if n is becoming large, it's tending to normal distribution. Even for Poisson, when lambda is becoming bigger and bigger, it's tending to normal distribution. So, irrespective of the probability distribution, if n is large, finally you get your normal distribution. So that is the idea of central limit theorem. Uh, Fine. So where is this? So we know this is true for x, which is a normal random variable. But central limit theorem is saying even if x is not normal, it is fine. But n should be large. If n is large, then you can consider this to be this in the sense this one, this right side, this one to be yes. So this side you can consider that to be almost normal, standard normal. That is central limit theorem. Fine. Uh, So yes, so approximately, so not exactly, but it's tending. If n is large, it's tending to this one. Fine. And we know expectation of x is mu, and variance of x bar is sigma square by n. We saw this so many times, but we didn't know which distribution. We just wrote expectation is mu and variance is sigma square by n. Central limit theorem is guaranteeing that it is normal for a large n. But if we know x is coming from normal distribution, then even this is normal distribution. But if x is not coming from normal distribution, then for a large number of n, this x bar will be a normal random variable. That is central limit theorem. Proof. We need proof. I don't think so. They're using MGF, so I don't. No, we're not proving anything. So it's fine. Let's skip the proof. Proof to the proof. No proof. Okay, thank you, thank you. Let me skip this. Okay, so if n is like around 25, 30, then you can say n is large enough. So doesn't have to be like 10,000 or something. Okay, and even it can be even 4 or 5. The distribution is symmetric if you have that information. Nice. And if okay, if x itself is normal, then n can be two or 3 as well. Nice. Mm, okay. So even see now every distribution can be normal. Even binomial will be normal when if n is very large. So if n is around 25 or something, probably you can say this is also normal, approximately, maybe. Okay. So so in that case, mu of binomial is np, and standard deviation is under root npq, right? Where q is 1 minus p. So it's the same thing now. They're using central limit theorem now. X bar minus mu by sigma. That is what they're writing. Are they writing X bar though? Wait, let me go back. I don't think. So okay, fine. I can replace X bar. What is that? The idea is this: if you have a random variable x, just subtract mu from it and divide by sigma. This will tend to sigma in the sense. Okay, I'll not write sigma. I'll write variance of x under root. This is expectation of x. This is much better. This will tend to standard normal if n is very large. So I can replace x with x bar. Expectation of x bar is mu. Standard deviation of x bar is sigma by root n. For binomial, what is happening? I can expectation in binomial is np, variance is npq, and standard deviation. This is what they're writing. That's it. So essentially, this is central limit theorem for large n. For large n, even if x is not coming from normal, but they have to be IIDs. They have to be IIDs, independent. Um, okay. Okay, how to apply central limit theorem? Okay, how do you apply? Let me know. Let's see how does this person apply. So write the random variable of interest y. So okay, so they're considering the sum of all the IID random variables. That is a random variable. Okay, fine. Then its mean is going to be n mu. Its variance is n sigma squared. Okay, nice, beautiful. Uh, so they wrote something like this. So y minus, I wrote the same thing, but oh my goodness, instead of y, I wrote x. So I think writing y is better. X means you get confused. X is the sample, right? So maybe write y. That is fine. Mm, I'll change it to y. I'll change this to y, 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 where y is nothing but summation of all xi's. Nice. Okay, so now you can say by central limit theorem, as n approaches to infinity, I can approximate it to standard normal. After you convert to standard normal, that is, and then you can use the Z table or whatever the table, the CDF table, to solve what happened. What is happening? To solve the problems. Okay, fine. Where was it? Here. Okay. I'm just going through things. Okay, continuity correction. Okay, I told that irrespective of the probability distribution, you can just say this is normal, this is normal, this is normal, and so on. But then normal distribution is a continuous distribution. What if my sample is coming uh, from discrete probability distributions? Now I'm saying that this will tend to normal distribution, which is a continuous probability distribution. So there's something called correction, continuity correction. So okay, they gave an example. Let's say y is binomial. Binomial is discrete. N is 20, so it is indeed a large number. So maybe you could use what central limit theorem. N is large, so you can use central limit theorem. Large enough, not 25 or 30, but still you can use it. Okay, so you define y is x1 plus x2 and so on. And what is binomial? Binomial is we've seen it's sum of Bernoulli. So each xi is Bernoulli. Parameter is p. P is half. Fine. So expectation of xi is p. Variance is pq. Q is 1 minus p. Okay, fine. So by central limit theorem, y minus n mu by under root under root what? What is the variance? Okay, variance of y is variance of x1 plus variance, so n sigma square. So n sigma square is variance. Under root variance is sigma under root n. So okay, fine. So sigma under root n. So y minus expectation of y divided by standard deviation of y. By central limit theorem, this will be nothing but the standard normal. So now I just have to use standard normal. So approximately, this is approximate values. Simple. So CDF of this one is my thing visible? CDF of this one minus CDF of this one. You'll get some value. And yes, what is phi of 0? Phi of 0 is 0.5. Because what is phi of 0? Phi of 0 is minus infinity to 0. What is the area? Area is half. So n is fine, small. 30 is large for some reason. You got 0.31. Here you got 0.45. So if you notice, the error is big. One possible explanation is binomial is a discrete distribution. Normal is a continuous distribution. So you might not get the proper values. So there is something called continuity correction. So what do you do? So instead of uh, instead of writing 8 to 10, you go to the left of 8 and right of 10 by half. So what do I mean by that? So if you want to find 8, or let's say if your interval is a to b, just go to the half by just go to the right by half and go to the left by half. So a minus 0.5. So now this is your new interval. Apparently, doing this will reduce the error. We will not look into the reasons. So, and since it is discrete, 7.5 to 8, nothing is there, and 10 to 10.5, nothing is there. So I can write it like this. There is no problem. Mathematically, there is no problem. But now my approximation to normal will change, right? So by doing this, you will get less error. The approximation will have less error. So 8 will become 7.5, 10 will become 10.5. You're increasing the interval now. This gave you how much? 0.4567. What was the exact value? The exact value was 0.4565. This is 0.4567. Very nice, very nice. So what does this mean? We've seen practically that error is reduced. We're not looking into reasons. We're not looking into the reasons. Whether you have to use continuity correction or not, uh, it is advised that you use continuity correction. But even if you don't use continuity correction, you won't lose marks. I think this is something which I heard from sir. I think maybe you could verify, but oh, the classes are done, right? You can't verify. Uh, but it shouldn't matter. It's not like if you use continuity, if you don't use continuity correction, you won't get marks. I don't think that is the case. So basically, this comes into the picture when you're trying to write a discrete random variable in terms of continuous random variable. Basically, binomial to normal or Poisson to normal. Maybe okay, fine. Poisson is discontinuous, discrete, right? So Poisson to normal also. No, 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 I don't want to go there. I should go down. Why? I can skip anyways. Where was I? Central. Down, 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 down. No, 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 not this one. Oh, yes, fine. So yes, so left minus half, uh, right plus half. So fine. Why half? Apparently that gives the least error. So for some reason, so I'm not going into that. So that's what. If you're on the right side, I mean maybe if you don't use the continuity correction also, it's fine. That is not a problem. See, in binomial, what does p of x greater than n mean? So strictly greater than n means it is greater than or equal to n minus 1. So when he says strictly greater than n, it means from n minus 1, all the other points. So since this is on the leftmost thing, you go left by half. So how do you go left by half? This point is nothing but n minus 1. Oh, did I write it reverse? Oh, my bad. My bad, my bad, my bad. How is this? Uh, if this is n, this is n plus 1. So you go left of n plus 1 by half. So what is that? N plus 1 minus half. Nothing but n plus half. So from the leftmost point, you're still going left. So that is why you got n plus half. So leftmost point means you're going left. It looks like you're going right because n plus half is to the right of n, but this is actually p of x greater than or equal to n minus 1, n plus 1. So n plus half is to the left of n plus 1. So we're not changing anything. If you're on the left side, you go left. If you're on the right side, go right. How do you know left side, right side? If this is your interval, then this is left side and this is right side. This has no right side only. Interval is like here. Fine. This is continued. I don't think you will be you will have to compulsorily use continuity correction. So I'm going ahead. Whoever got it, it's fine. Fine. Okay. More questions. More questions. More questions. Interesting. That's a nice number there. Okay. Is there anything else? No. What else is in the portion? Did I get any messages? Let me see. Okay. I think I will do 9 and 10 and probably stop. How many? Oh, it's 44. Hmm. Let's see. Okay. You have only two distributions, yet you have 44 slides on this. Okay, see, is it in the portion? The multinomial. Oh, you do have it in the portion. So multinomials are okay. Sir also did this, right? So before that, we did function of random variable. So even we will follow the same order. Then we'll first do Okay, wait a minute. Function of this is 67. I mean, fine. We'll just go four cases. Fine, nice. Discrete one dimensional, continuous one dimensional, continuous one dimensional, continuous two. Okay, fine. We'll just go. So it's like we have some random variable, we have some function of random variable now. We have to find the PDF, CDF, or whatever of that function of random variable. And discrete case is simple. Discrete case is just substitution at this point. Uh, Need an example. Okay, so this is a discrete case, right? So they told x is a Poisson random variable. Poisson is a discrete. So like this is how you get indirect questions. They're not asking you to they're not asking you PMF or CDF of uh, Poisson, but they're making you use Poisson in other questions. So this is the way of asking indirect questions. So this is what I was trying to tell when indirect questions are they can okay fine. Uh, y is under root x. Is that continuous? No, because x itself is discrete, so y is also discrete. So this is discrete case. Discrete case, simple. You can okay. First, what you do is we know p of x. P of capital X equal to small x is lambda power x e power minus lambda by x factorial. Fine. And x is 0, 1, 2, 3, 4, and so on. How to write P of capital Y equal to small y? We want this. We want the PMF of capital Y. Simply simply rewrite capital Y in terms of capital X. Capital Y is root x. So root capital X is equal to small y. So that's the first thing. When you're dealing with a discrete case, simply replace, first write down this P of capital Y equal to small y. In the question itself, we know what is capital Y in terms of capital X. Just put that here, and now you start solving the equation. So some function of capital X is equal to small y. Here the function of capital X is root x. Just rearrange the terms. What will you get? Uh, Rearrange in the sense, until when? Until you get something like capital X equal to something. Because if you get capital X equal to something, we know what is capital X equal to something. So capital X equal to something is 4 power something e power minus 4 divided by something factorial. Here the something is y square. So 4 power y square e power minus 4 something factorial. Something is y square. So y square factorial. So discrete case is simple. You simply write P of capital Y equal to small y. Replace capital Y with the function of capital X and keep rearranging until you get P of capital X equal to something. That something will be in terms of small y only. So some function of small y. And then you have the PMF. They wrote PDF, it's PMF, printing mistake, because discrete, right? You don't have a density function, you have mass function. Even here, it should be PMF. No one noticed properly. PMF of X, PMF of Y. The question is correct. PMF of Y. Okay, anyways. Okay, what is capital S of X? Capital S of X is the range of X. X is going from 0, 1, 2, and so on. Range of Y is under root 0, under root 1, under root 2, under root 3, and so on. Okay, so after you write P of Y equal capital Y equal to Y, you should also write the range of Y. So don't leave it empty. So after you write 4y square e power minus 4 by y square factorial, you should also write what is the range of small y. Small y is basically the under root of x, right? So root 0 is 0, root 1 is 1, root 2, root 3, root 4, and so on. If you don't mention the range of small y, if you simply write uh, p of capital Y equal to y is this one, you might risk losing marks. And what if y is not equal to any of this? It is 0, so maybe you could write that as well. Uh, uh, Otherwise, like probability is 0 otherwise. So for small y equal to this is the probability. For small y equal to 0, 1, root 2, this is the probability. Otherwise, probability is 0. So you can write it that way to be on the very safe side. You'll have to write when is it 0 as well, because 0 probability is possibility. Okay, enough of example. This is discrete case. Discrete case is simple. Uh, See, same thing, same story. You first write P of capital Y equal to small y, replace the capital Y with the function of capital X, rearrange until you get P of capital X equal to some function of small y, substitute, done. No, not done. You have to write the range of small y now. If X is 0, 1, 2, 3, what is Y going to be? Y is going to be a root of them, right? Is it the same function? So y is x square. So y is going to be 0 square, 1 square, 2 square, 3 square. You have to write the range as well. So where 0, 1, 4, 9. Fine. Y is 0, 1, 4, 9. I think enough of discrete case examples. You can, oh, fine. Only two examples. Continuous case. Here comes uh, the Jacobian. We'll see. In two-dimensional Jacobian. Okay, we'll find the one-dimensional Jacobian here. Uh, okay. There is some random variable, capital Y equal to A, capital X plus B. A is non-zero, okay. Let us assume capital X has some CDF, capital F, X. and we want to find capital Fy. So we want to find the CDF of y. Since x is a continuous random variable, y will also be a continuous random variable. Uh, okay, so what are they doing? So what are they doing? So CDF of small y is nothing but probability of capital Y less than or equal to small y. So I think they simply replaced capital Y with what? What is capital Y? A capital X plus B. So A capital X plus B less than or equal to Y means Y minus B by A. Okay, but is that right? There should be. Okay, that is just a CDF. This is just the CDF, so there is no problem. But let's see what will happen if you differentiate it. We'll see. So this is very similar to the method that we did, right? What did we do? Uh, you you just have, okay, fine. Let me write it here. Y is ax plus b. It is given that this is the CDF of x. We have to find CDF of y. CDF of y is nothing but probability of y less than or equal to small y. I know capital Y is ax plus b. So I replaced capital. See, this is the same procedure almost. So I have to keep rearranging until I have small capital X here. So when will that happen? I have to write y minus b by a. So this is nothing but the CDF of y minus b by a. That is what is that's what is written here. Okay, okay, okay. Reload. No, no, not yet, not yet. No, no, no. Where am I? Where was I? Here, okay, fine. I here, here. So fine. So CDF of capital Y is CDF. Okay, capital F Y is nothing but capital F X of Y minus. Okay, this is fine. We understood this. On the other hand, okay, so mind you, we are able to send A to the other side only if A is positive. This is only if A is positive. So two cases. If A is positive, is if A is negative. If A is positive, this is nothing but P of X, and if A is negative, then you'll have the oh, see, if A is positive, then sign won't change. If A is negative, sign will change. So this is nothing but CDF. You can use CDF of the X CDF we can use, but you have to change this a bit. You have to write this as in order to write it in terms of the CDF of X, you have to change it. So this will be 1 minus fx y minus b by a. So two cases, a positive, a negative. A 0, we at least, oh, a is non-zero, I think they've mentioned, no? A is non-zero. Did they mention? A is non-zero, so we are least bothered about it. Uh, okay, so two cases, we have two things. Fine, we'll see what are they doing with it. We can obtain the PDF of y by differentiating this CDF with respect to y. So differentiate with respect to y. Okay, so if you want to find uh, CDF of y, you will have to differentiate, right? So you have two cases. If a is greater than 0, if a is less than 0. If a is greater than 0, you simply differentiate this. You get, what do you get? Differentiation of this is nothing but the PDF of x only. And then you have to do the inner differentiation as well, right? So you will get 1 by a. Differentiation of y minus b by a with respect to uh, so I'm just differentiating this with respect to y, and I'm going to differentiate this with respect to y too. So there you'll get 0 minus fx minus ba 1 by a. So finally I can write that PDF of y. See, if a is positive, this is there. If a is negative, there is a minus sign. So I know that uh, not a, take okay, A. So if A is negative, then mod A is minus A. If A is negative, mod A is minus A. So minus A will replace it by mod A because I know here A is negative. And positive one also it's fine. So if A is positive, mod A is A. So I can write these two lines in the same line now. F of x y minus b by a 1 by mod a. This is the PDF. So in PDF, some extra term is coming. If they ask you to find the CDF, we're just done. Just have to write this. There is for A positive, for A negative, you have two different CDFs. So this the first method is this one. From CDF, we are trying to write PDF. How? By finding CDF first and then differentiating. That is the first method. Okay, more examples. So they gave you a PDF. They already gave you a PDF. Now they're asking you to find. Okay, what is the equation for? Okay, so if you notice, what is y? Y is a linear transformation of x. Y is a linear transformation of x. So, and this is the continuous case. So here, y is a linear transformation of x. So we can directly use the formula. So what is the formula? 1 by, so PDF of PDF of y is nothing but 1 by mod a times PDF of y minus b by a. So if you use that for linear transformations, this is strictly linear transformation. So f of CDF of small y is nothing but 1 by mod a x ka PDF I will use y minus b by a. We just found that, and they're telling that x is Gaussian, right? So normal mu sigma square. So what is my f of x going to look like? What is my PDF of x? It will look like 1 by sigma under root 2 pi e power minus half x minus mu by. This is the PDF of normal distribution with mean mu and variance sigma square. So what is my f of y? What is my PDF of y going to be like? Y is a linear transformation of x, so I just have to uh, use this. So it will be 1 by mod a. Uh, so what is this going to be? So my x, I have to replace x with y minus b by a. I have to replace x with y minus b by a. E power. So instead of x, I will have y minus b by a. That's it. So directly, directly we wrote the PDF of y. How? We use some formula. Linear. This is only for linear transformation of y. So y is ax plus b. We are, what is the context here? X is a continuous random variable. Y is a linear transformation and hence is also a continuous random variable. We have the PDF of x, so now we wrote the PDF of y. How? Using this linear transformation only. If y is x square, don't use this. That will be a blunder. This is only for linear transformation. You don't have to remember also. See, this process is simple. You don't have to spend much time as well. In case you have a lot of space in your head, maybe you could memorize, but I wouldn't suggest that. If you understand what to do, how to do, where to do, why to do, I think everything is fine. Okay, moving on. So this is how you get the PDF directly. Non-linear. Okay, fine. So here comes non-linear. Y is x square. Uh, why is x square is a very popular question. It keeps popping up here and there in the tutorial, in the quizzes. This, I'll be uh, no, I'll not comment on Endsem. I don't know. I don't know if y equal to x square, if this exact thing is going to come. Because non-linear function mean y equal to x square. This is what people love. So I don't know. Fine. So y equal to x square, non-linear. So you can't use the formula that we used before. Okay. So y is equal to x square. What do you do? Then you do the same process as before. They gave you okay. What is given? CDF and PDF is known. Mm, I mean, you can do the same process. You can do the same process. Do you want me to do or not? Fine. Okay. Let me do one non-linear and then I'll just move on. Maybe just this. If I say y is equal to x square, and I said I have CDF of x. I also have. I mean, if I have one, the other one is automatically with me, right? So, okay, let's see. What am I supposed to do? I want to find CDF of y. What does this mean? Y is less than or equal to small y. What is y? Y is x square less than or equal to small y. But now, if I say x square is less than or equal to small y, what does this mean? If I draw this, uh, let's say this is y and this is x. So this is nothing but y equal to x square, no? This is y equal to x square. No, oh my goodness, y equal to x square looks like this. So this is y equal to x square. When I say x square is less than or equal to some small y, so this is some small y. This is like okay, so y is some small y. Uh, okay, let me say this is some function. Fine. Oh, I will not get into the details. So the idea is this one. See, x square is less than small y. So it is basically this entire region. X square is less than y square. So it means if you try to split this, you will get two answers. Uh, what is this? Where is this point? This point is, where is this point? Minus root y, right? Yes, and this point is root y. The problem here is if you look at a certain y value, you will get 2 points, like two input points are there. So for one y value, you have two inputs. So this is like a many to one function. It's not a one to one function. So what will happen in this case? So it is like p, where should x be? So x is either here or here, so two places, right? Mm. And I'm saying less than or equal to. Okay, where is x square less than y region? Okay, this region, fine. So x must lie, fine, let me just see. I think there are some theorems that will help us. We will wait for the theorems. Or should I just read this event occurs and okay, fine, fine. So this is nothing but this region, no? What is this region? This region is nothing but minus root y. Nice. So probability that x is in this region. Fine. So I can, how do I write this? This is nothing but CDF of x root y minus CDF of x, x CDF of minus root y. Simple. I didn't do anything. Whatever I did in the discrete case that I'm doing here. Mind you, I'm using CDFs. That's why I'm able to do this. PDFs is a different story because you get some factors. Like previously we got 1 by mod A and all that. So PDF is strange. So we will look into it. So, okay, this is CDF. This is fine. This is CDF. What about PDF? So PDF is nothing but differentiation of this with respect to y. So if I differentiate this, what will I get? I will get this one, and differentiation of root y is nothing but what is differentiation? Yeah, so you will get 1 by 2 root y. So same story here. What will you get? You'll get this one, and then you'll get minus 1 by 2 root y. Finally, you will get 1 by 2 root y f of x root y plus, no, not f of x, fx root y, and then fx minus root y. So this is your PDF. See, you're getting two. You're getting a sum because there are two inputs. So for one y, you have two inputs. So that is the meaning. For one y, you have two inputs. That is why you are getting a sum. And there is this additional factor. Fine. We got CDF, we got PDF, we got the same thing. And y should be greater than 0 because if y is 0, then denominator will it will start crying now if y is 0. So you have to mention the range as well, right? So you wrote the PDF, y should be greater than 0. What if y is equal to 0? If y is equal to 0, look at this graph. If y is 0, what is the PDF? 0, because y equal to x square. If y is 0, what does it mean? X square is less than or equal to 0. That means x square is equal to 0. So when y is 0, it means x square is less than or equal to 0, which means x is 0. X is 0 means x is 0 means what is okay, we don't have the exact PDF, do we? So y equal to 0 means x is equal to 0. So x is equal to 0 means I think you can write this f of x at 0. This is when y is 0. Now we are foolproof. It is fine. This is like to be on the very, very safe side because we know if y is 0, what is going to happen? If y is 0, it means we want to find uh, So we want to find this now. So this is nothing but p of x square less than 0. This means p of x equal to 0, because x square less than or equal to 0 means x has to be 0. This is nothing but, and mind you, x is continuous. So if x is continuous, at a single point, probability is going to be 0. So this is going to be 0. Nice. So 0. And can y be negative? No, y can't be negative. That is not the range. So I can simply write otherwise. Nice. Okay. You can do, okay, see, now they'll have y equal to x square. I think maybe, I think, I don't know. We'll get y equal to x square or maybe something else. But if you know the procedure, I think you're good to go. Uh, I will not solve this example. Just you can just see. And yes, CDF also, right? CDF like this. Where is it 0? Where is it 1? Where is it the function? So here also, careful. The CDF is, where is this? The CDF, this is CDF when, uh, uh, okay, let me, down, down, down. Okay. So how do you write the CDF? CDF, it is 0 somewhere, it is something elsewhere. When is it 0? When, okay, fine. You can write 0 part later as well. That is not a problem. When y is 0, what is happening? When y is 0, that's what. It's the same story. So this is when y is this one and 0 otherwise. Nice. Do we get a 1 here? No, I don't think so. When will the CDF be 1? Okay, see, this is non-linear. You have x bar n. Are you sure we won't get a 1 anywhere? Oh, it is 0. I don't see the reason. Fine. Okay. Enough thinking. Anything else here? Okay, mod x. Interesting. This is mod x is nothing but uh, plus plus x if x is greater than 0, minus x if x is less than 0. You can solve it. Change of variable technique. What was the previous technique? I don't know. Right. Maybe finding from CDF. That was a technique. Here you have nice, beautiful theorems to help us out to find the PDF directly. So we are still in one dimension. So this is your one-dimensional Jacobian. Uh, let x be a continuous random variable having probability density function small f. Suppose g is strictly monotonic, okay, increasing or decreasing, differentiable in this continuous function. Then the random variable y defined by this function g of capital X has a probability density function given by something. Okay, let's see. So you have y equal to g of x. G is mm, differentiable. G is and therefore continuous. If it's differentiable, it is continuous. Anything else, it is monotonic, right? It's either like strictly increasing, or I mean, strictly increasing, or it is strictly decreasing, whatever. Anything else? Nothing. It's okay. G has some probability density function. Okay. We know that there is some PDF for X. Now we have to find the PDF of Y. So PDF of Y will be basically uh, it will be PDF of X into you take the modulus of it's either dx by dy, or you can either do this. You can do this one by dy by dx. So it's like there's this property. The property is dx by dy is equal to 1 by dy by dx. There's this property. So now the thing that you're supposed to do is you have to write x in terms of y. So x will be if y is equal to g of x, that means x is equal to g inverse y. How do we know an inverse function exists? Because we are ensuring that the function is monotonic. If the function is monotonic, you will have inverse. But strictly, all monotonic functions have inverse functions. So this is guaranteed. So now what will happen? This will you can rewrite this as this entire thing. You can rewrite this as x is nothing but g inverse of y. So f of x g inverse of y, and x is nothing but g inverse of y. So g inverse of y. See, it's just this thing. Uh, I'm just replacing x with g inverse of y. Or else I can do d by dx of y. What is y? Y is g of x. So anything works. So this is there in the slide, so you can see. You, fine. However you want to remember, you can remember. So this is there in the slides. So f of x, fx fx of g inverse y, and then modulus. No, not yet, not yet, not yet. No, 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 no. Here, please. So this is a theorem. You just this is going to help us. And the range, yes. What is the range? Range should be given in terms of y because our PDF is in terms of y. So y should be equal to g of x, or else it's zero. So y has to be g of x, or else it is zero otherwise. So this or this, or else it's zero otherwise. These two things are the same things. Okay, there's some theorem. If you look at an example, maybe then you will be able to solve. We don't have to look at proof. Mm, you don't have to look at proofs. You don't have to look at proofs. Okay, the intuition behind the mod is that your PDF should not be negative. No, probability can't be negative. Okay, some example is here. Okay, what is the example here? They told y is equal to e power x. So you have some function of x. So you can use the theorem. You can use the theorem. So uh, f f capital Y of small y, the PDF of small y is nothing but you just apply the theorem. So what is G inverse here? G inverse is ln. So if y is equal to e power x, x is equal to ln y. So G inverse is ln in this uh, example. You can solve it. That is not a problem. So what were the conditions? G is differentiable and hence continuous, and G is strictly increasing or strictly decreasing. So it's a one-to-one function. There are no. It's not like x square. X square is not strictly increasing. X square is first decreasing and then increasing. What to do in those cases, we will see. I mean, we've seen how to deal with y equal to x square. This is another method. There is another method. There are some theorems that will help us. Theorem. Uh, Multiple solutions. So yes, so when you have multiple solutions, that means when will you have multiple solutions? Only if it's not strictly increasing or decreasing. Like x square, you see. Uh, okay. Anyways, we'll just see. Like okay, we'll just look. So this is when you'll have multiple solutions. If I draw a horizontal line, I will get multiple x values. But in a strictly increasing and decreasing function, if I draw a horizontal line, I will only get one intersection point. So that is what they're trying to say here. So there's one theorem for that. Okay, this is the theorem. The theorem is basically the old theorem only, but now what you do is you divide your function into multiple parts such that in each part the function is either strictly increasing or strictly decreasing. So in this case, the function got divided into three parts, and in each part it is strictly increasing or strictly decreasing. It is monotonic, and then you have differentiability. So you are trying to satisfy the conditions, differentiability, and then the function is monotonic. Okay, so what is a summation? Like, what are you summing? Uh, you're basically adding, like, you solve for each part. You have three parts here. No? You solve for each part and add all of them. Then you will get your solution. That is the summation, basically. Uh, for example, if you look at the y equal to x square problem, we can solve it using this approach, this theorem. So when you say y is equal to x square, and let's say I know what is let's say I have the PDF of x. So now I'll use the theorem. So what does the theorem say? No, first of all, how does x square look like? Y equal to x square looks like this. Is it strictly increasing or decreasing? No. So what I'll do, I will divide this into two parts. This is one part, this is the second part. In each of the parts, the function is monotonic. It's like strictly decreasing here, strictly increasing on the right side. Now I will use a second theorem. The second theorem is you sum the things, right? So this is nothing but summation fx dx by dy. So I will have two things, two parts. So I equal to 1 to 2. Now it's up to you. If you want to do dx by dy, you can do that, or else uh, in the denominator you can keep dy by dx. It is absolutely up to you. But let's try dx by dy. So okay, I have y equal to x square. So what does that mean? If I differentiate it with respect to y, what will I get? So I'll get 1 equal to 2x dx by dy. That would mean dx by dy is 1 by 2x. So okay, so I'll substitute in this summation. Okay, so let's say I have one y value. This is y equal to x square, no? Then what are my x values going to be? So here you'll get root y, here you'll get minus root y. So these two are the values. So my x1 is root, okay, x1 is minus root y, x2 is root y. So fx, because I have to write x in terms of y, no? So x is nothing but plus or minus root y. So you can get mathematically as well. So one x is root y, the other x is minus root y. So I told part 1 is left side. So first I will write x1. x1 is minus root y. And what is dx by dy? 1 by 2x. So mod 1 by 2 minus root y plus fx root y. The other x is root y, no? So 1 by mod root y. So if you simplify, what are we getting? We are getting the same thing. Whatever we got before, we are getting the same thing now, aren't we? Uh, See, we got the same thing. So whatever procedure it is, you get the same answer. This is for our beloved y equal to x square. You can do it for other questions as well. Sine x. My goodness, you get multiple solutions. Okay, fine. So they defined an interval, so we are safe. But still, you'll have to be careful. Within that interval, how many times is the solution repeating? You have to check. So I will not look into examples. Okay, they've given the graph. So how will you divide this? From minus pi by 2 to pi by 2, it is strictly increasing. From pi by 2 to pi, it is strictly decreasing. So two parts. It is differentiable, it is monotonic. Nice. Just solve it. You can do that. Okay, all of these are examples. I think. Nice, nice, nice. Beautiful, amazing. Okay, well, this is the third case, right? No, fourth case. Fourth case, yes. So the last case. After this, we have. Oh, this is the first maths video, right? So, okay, nice. We covered a lot of things. We covered a lot of things. So, in the next maths video, we will cover the bivariate and multinomial and bivariate normal distribution. I think math was the fastest. Physics and opti was kind of jagged. Physics was more laggy. Math is nice. Nice. Anyways, I'll just try to finish this, but it's already 8 p.m. I was supposed to stop at 7:30. Okay, let's see. Now, in one-dimensional case, that we got something like mod dx by dy, right? That was the one-dimensional Jacobian. Now we have the two-dimensional Jacobian. Let me just write the notation for Jacobian so that people can do away with their confusion. But before that, let me see if I got some messages. Messages. No messages. Okay. Jacobian, fine. Okay, wait, sorry. Okay. So, Jacobian. Jacobian. Okay, wait. Before that, let me write the context. What is the context? So, okay, y1 equal to g1 x1 x2. Okay, y1 equal to g2 this one. And inverse. Okay, inverse is h. Fine. What is the context? Okay, so there is a jointly continuous random variable, joint probability function. Okay, So I will just write whatever is the premise. So you have y1, which is a function of x1 and x2. You have y2, which is a function of x1 and x2 as well. And let's say the solution of x1 is some h1, solution in terms of y1 and y2, and x2 is nothing but another function, but okay, fine. So it's like if you solve this, you will get this. So fine. Now, now we'll look into the Jacobian. So Jacobian of uh, if someone's writing the Jacobian x1 x2, it means you want to differentiate with respect to x1 and x2. And what do you want to differentiate? You want to differentiate this one. So you there is alternate notation as well. You can write this as a y1 y2 x1 x2. This is just notation. So the main thing is the determinant. So what you're supposed to do is uh, do y1 by do x1. So the first column you differentiate with respect to x1. The second column you differentiate with respect to x2. Is I hope I'm correct. So let me just verify. Let me verify. Yes. Nice. So y1 is nothing but g1. So you can replace this with g1. That is fine. In the slides, you have do g1. That is also fine. That is absolutely fine. So this is Jacobian. If someone writes Jacobian y1, y2, so you would want to do the exact opposite. So if you have Jacobian of y1, y2, it means that will go in the denominator. Basically, not denominator. I mean, you're going to differentiate with respect to y1 and y2. So first you differentiate with respect to y1, then you differentiate with respect to y2, and x is nothing but h, so you can replace. You have to replace them. So you have functions, you can differentiate. You get Jacobian. So nice notation, nice. The determinant, nice, beautiful. But I think it's getting late for me, so I will start from here in the next video. I am hungry, so I'll go have dinner now. Okay, fine. I'll just stop the live stream abruptly, just like this. Meet you in the second. Where is this? Second part of this. End.